So we can pause and start and stop the recording as and when we want. So that's very convenient.
Okay, so it's time to start the WAT 2021. So, okay, good morning and good evening, everyone. I'm Toshiaki Nakazawa from the University of Tokyo. I'm one of the organizers of WAT 2021, the ACE workshop on Asian translation. So, can you hear me? Yeah. Everyone.
Yes, we can see you.
Okay, thank you very much. Okay, so WAT 2021. So the what is a workshop on Asian translation, which focusing on the Asian languages. And in 2021 WAT, we have 2 invited talks and 5 research papers and 2 findings papers from ACL. And this time we have 14 shared tasks, and we include 18 languages, and most of them are the Asian languages. And it's very happy to have the 26 participants for the shared tasks this year. There are a lot of participants. And this is a timetable to today's workshop. We have a very interesting program here, starting from the invited talk by Francisco Guzman from Facebook. And then we have the share task 1 session. And then we have the second invited talk by Graham Newbeck from CMU. And we have research paper session and lunch break, share task 2, research paper 2, and the share task 3. So we have a lot of items today, starting from 7 a.m. in Japan until the 5 p.m., 5:30 p.m. And yeah. So here is a list of participants for these shared tasks. We have a lot of participants worldwide. Yeah, this year we have the, okay. Yeah, a lot of institute from the worldwide, like Myanmar, Switzerland, Singapore, Korea, India, Poland, and Denmark, and something like that. Yeah, thank you for participating in the shared tasks. And here is a list of participants for each shared tasks. The check mark indicates that this team joined this shared task. Yeah, and we have a lot of participants for the INDIC 21 INDIC multilingual translation tasks. And also we have multimodal translation task. And this year we have the 3 new translation tasks named restricted translation task, which will be presented in the morning session after the invited talk 1. And here is the research papers and findings papers. We have 3 and +1 presentations in the research paper 1 session, and 2 + 1 papers in the research paper session 2. And yeah. Okay. So please enjoy WAT 2021. And next will be the invited talk 1 by Francisco Guzman. And Raj will chair the session. Thank you.
Good morning, good evening, good afternoon. So I'll be the chair for this invited talk. It's my pleasure to invite Paco Guzman and Angela Fan to talk about their awesome work on Flores 101, which is a large-scale data set for machine translation evaluation. Paco Guzman is a research scientist manager at Facebook AI, and Angela Fan is a PhD student at INRIA Nancy and a Facebook AI researcher as well. So please tell us about your awesome evaluation data set. Looking forward to the talk. Thank you.
Can you hear me now?
Yes.
Perfect. All right. Thank you, everyone. And thank you for waking up so early in Japan. It's 7 a.m. So it's brutally early. So thank you so much for the invitation as well. Today, we're going to be talking about massively multilingual low resource translation. And it's a joint work with my colleague, Angela, who is right there, and myself and the Flores team. So let's get started. So translation connects people. Language is something that is really personal, right? Language helps us to connect with the people that we love and with the knowledge that we seek and with many things that we care about. But sometimes language can be a barrier itself. If you think about a grandma and a grandchild that are living in different societies, speaking different languages, they may not be able to communicate because of language. Or somebody who's trying to sell a product across borders, you can see that language may be a difficulty trying to reach customers that may be interested in the product, but may not speak the language of the seller. And machine translation can help us to bridge that gap. Machine translation helps us to very quickly translate between one language and the other. And machine translation has been helping us already to reach people that we care about. And Facebook, we have this feature, which is C translation, which allows people reading Facebook posts to connect with what the information of a poster somebody is posting in case that they do not understand the language. And machine translation has been making a lot of progress in the past years, particularly in what we call the high resource languages, languages like French, for example, here. And this is because machine translation is a supervised task and would require a lot of training instances to be able to reach a high level of accuracy. But what happens with languages that do not have those high resources, right? Thinking about this, for example, if you look at this graph from our colleagues at Google, they plot how many training resources there are per language pairs. Now, thinking about how many languages are there in the world, you can think about maybe having around 6,000 languages, give it or take, right? And not even 200 language pairs have more than 10K parallel synthesis. This is a tiny amount of data, right? Which means that learning to translate is going to be very, very difficult for the long tail of languages. So how do we get there? Now, language low resource translation is not only difficult because of the amount of resources, but because of other added aspects. So for example, language similarity. Some languages are closer to each other. Think about Belarusian and Ukrainian, and they may be able to leverage resources from one another. The same with Nepali and Hindi, right? Nepali can borrow resources and do some transfer learning thanks to resources from Hindi. But some languages are maybe isolated, more isolated, or may belong to a family that itself is very, very isolated. So that supervision may not be there. Now, the other aspect is domain. We may have a lot of data, but it may be in the wrong domain. Think about if you want to translate news, but then the data that you observe, you can obtain is mostly the Bible or IT manuals. And the third aspect is evaluation, right? So without clear evaluation and reliable evaluation, we do not know if we're making progress in the low resource task. So this is why this is very, very important. This is something that we addressed initially with the Flores data set, first for Nepali English and Sinhala English. We had a first experience translated generating these benchmarks, and it was really a learning experience for us. The second iteration included Pashto English and Khmer English, but in total, we're covering 4 different languages. And what about the rest of the languages? What about the rest of the world? So based on this question, and this motivated us to create the next iteration of Flores, which we call Flores 101. So this is a benchmark data set with 101 languages that covers a large variety of languages around the world. Now, at a glance, what is Flores? So Flores is different from the Flores 101 is different from the previous iteration, in which each sentence that we included in this data set was actually handpicked from different documents across different sources. In total, we had 3,000 sentences. On average length is 22 words. And from each document that we sample, we took between 3 and 5 sentences. We kept the whole document context because we think that in the future this can help document level machine translation. And we also, well, we are translating 101 languages, as I said before. Now, we have 3 different sources of data for this data set that present different domains. The first one is Wiki Junior. So Wiki Junior is a part of Wikibooks. It's open source as well. And this is related to, it's for children, it's dedicated for children. So it has a more simple version of English, but it's dedicated to relevant themes like science. Here you have an example of something related to chemistry, in which the color of a compound can change depending on the alkalinity or acidity of the compound. Then we have Wikivoyage, which is a collection of travel information from different regions in the world. And when we did the sampling, we made sure that different regions of the world were equally sampled, from North America, South America, Asia, Australia, etc. So we wanted to have a good representation. And here you can find information about history of places or tourist attraction, etc. In this case, for example, we have one text related to the Dominican Republic and its history and how it was first inhabited by Taínos and Caribs. And the last one is Wikinews. So Wikinews is news domain, and you have a different types of news. Here we have a sample with something related to business news. So why do we choose such the different domains? Is because we want Flores 101 to last for a long time. Creating these data sets is time consuming and really, really expensive. So we wanted this data set to last for a long time. And having a diversity of domains prevents us from overfitting to a particular domain. Now, we have a different, variety of topics. Travel is the most common topic that we have, around 40%. But again, within travel, as I mentioned before, you have a lot of diversity coming from places. And this is very nice because you have name entities from places like the Caribbean or Africa, etc. So this makes it a little bit more challenging. We also have politics, we have science coming from Wikijunior, sports, etc. We also have a large and quite a number of other topics, and you can take a look at the paper for more details. Now, just sampling is the first step, right? We wanted to make a very rich and diverse data set, but then comes translation. And I wish it was as simple as just translating something and basically getting the translation and call it a day. But it's actually more complicated than that. And this is something that we learned when we did the first iteration of Flores, in which we realized that the maturity of the translation pipelines for lower resource languages is not there. So we had to focus a lot in quality. So for this, the first step was to select the right service providers. We did pilots to ensure the quality across different languages. And then we divided the workload to the 2 best language service providers that we identified. And then, we had automatic checks. This is something that we learned from doing Flores, the first iteration. And the problem is that even if you have certified providers, they outsource to translators, to freelancers sometimes. And what we can see is that, we need to start checking for the quality of the translations before looking into the translation itself. So looking at the length ratio, making sure that translations are complete, for example, making sure that the translations are not copied from the source, making sure that the translation that we're getting is in the right language, whenever we can check that, right? And the fourth point is making sure that this is not a translation that comes as a copy of a public translation engine. And this may sound obvious, but it is not as obvious as we initially thought, because if you think about it, translation, machine translation is so embedded into the professional translators pipeline. People right now do a lot of post editing. So they take a first iteration coming from a machine translation, and then they just post edit it, right? But if you think about the purpose of Flores and why do we care about quality, is that we don't want to bias machine translation or the progress of machine translation towards one specific translation engine. So we had to put checks in place. And here, just to give you an idea of what we were dealing with, you have this blue score, so we call SP Blue, which is a blue score at the sentence level based on an SPM tokenization, and you can read more about that in the paper. But we are comparing here two different languages, translation from English into two different languages, one in gray, one in blue. And the one in gray, it has a high proportion of sentences that overlapped according to blue, got a blue score of 80 to 100 with a public translation engine. So what it is telling us is basically the whole body of this language is coming from either post edits or direct translation from an public engine. So this is very, very problematic. So we had to implement these checks so we can reject these translations, send them back to the translators. And once that was done, we then proceeded to human evaluation. We hired a third, an independent language service provider who did all the checks of translation quality, following an MQM style type of translation evaluation with 9 different criteria and different levels of severity. So what this gives is, at the end, you can assign a score for the whole batch of translations for a specific language. And if we set a threshold of 90. So 90 out of 100, if we get the quality above that, this data set is ready for publication. If it's not, it goes back to the translators and needs to undergo post editing. So the translators need to fix it again. Right. So, and one may think that only the low resource languages have problems in quality, but actually, what we found that was not really the case. We saw languages like Lao having very high level of quality, and other languages like Wolof and Khmer at the other side of the spectrum. So, being low resource is not the only aspect that determines the final quality. So with this data set, is a multilingual data set that we can start exploring a lot of aspects of multilingual machine translation. So what have we learned so far with Flores? And I'm going to make a sample of the studies that we run in the paper, but for more details, I really invite you to look into the paper. So in M2M, we expanded the model, M2M 100. We expanded it with additional languages to cover the corpora that the Flores 101 corpora. These models were trained with Mind Data and Opus Data, and we released 2 different model sizes, one 615 million parameters. That is the one that we're going to be talking about in the results. So let me go to the results. The first question that we ask is, okay, does training data, given that Flores is comparable across all languages, we can compare what is the performance of different languages depending on the training data, amount of training data that they have. And here, the first thing that we realize is, well, more data is always better, right? This is something that we kind of, this is not news. This is something that has been observed before. But something more interesting is in this region here. So these are languages that do not have a lot of data, but still are performing really well. And these are languages, for example, like Afrikaans. It doesn't have many resources, but shares a lot of features with Dutch language, which is higher resource, and other Germanic languages. right? Languages like Serbian, like Croatian, are also in this part of the graph. So it tells you that the sharing language family does play a role, especially if you share a lot of resources. And then you have these languages right here that are not reacting, let's say, to the amount of training data. And here we have languages that have unique scripts like Georgian and other languages that, on top of being having their own script, are morphologically rich, agglutinative, like Tamil, and this makes them harder to translate. Now, we also analyze the performance by language family, and here we provide a quick overview of that. In this table, on the left is the language family we're translating from, and on the top is the language family that we're translated into. And we can see the number of languages in that family and the blue scores, the average blue scores for translated from and to language families. And the first thing that we can observe is that certain language families that tend to have more data tend to do well. It's better to translate within that language family. But once we move away of those higher resource language families, we have that translated into the Germanic language family is one of the that it provides the best results. Thinking about this is English is part of the Germanic family, and most of the resources that we have, the training data that we have, is for pairings with English. So, for example, Tamil English, right? So this is not so surprising, but it explains that data plays a big role here. One interesting bit of information here is the Turkic languages. So they do better translated in the Balto-Slavic languages. And one possible theory here is that many Turkic languages in Central Asia have a tradition and influence from Russian, right? So this could explain why this is we're seeing the improvement in performance here. On the other side, the worst performing languages, we have the Nilotic, which are African languages, the Atlantic Congo languages. That includes languages like Igbo, Yoruba, and Fula, and they have very few resources, right? The whole family is very resource poor. We also have the Dravidian languages, the Southern Indian languages, which each one has its own script. And as I mentioned before, they are agglutinative, tend to be agglutinative. And then we have other Bantu languages. So languages that are really hard to translate. Translated from languages, we see a very similar picture. And again, I invite you to look at the paper. Then performance by resource level. Here we took a look at very low, medium, and high resource languages. And we just divided that by the amount of resources that we have. And what we observe in general is translating from or to higher resource languages yields the best results. There's no news here. But what is interesting, and I want to draw your attention to, is that translating from very low languages, it's very different than translated into very low resource languages. So, for example, translated from, you get an average of 5 blue points. Translated into, you get an average of less than 3 blue points, right? The most important part here is the delta that exists between translated into very low resource languages and high resource languages, which is about 15 blue points or 14 and a half. And then translated from very low resource languages and from very high resource languages, the delta is about 10 blue points. So this is telling us that there's some ways to go into improvement of our decoders. And the last two things that I want to discuss with you is the characteristics of the Flores data set and how they impact performance. We analyzed the sentence length, and we saw that there's actually not a lot of bias towards specific set of sentences. We have short, medium, and long sentences, and they perform at about the same level. So here I put an orange band that is about 1 blue point. And you can see that there is actually not that much difference across the different length of sentences. The same can be said about the different domains. So we see that Wikinews performs better than Wikivoyage, but the difference is less than 1 blue point on average. So we don't see a strong bias towards the domain. So now with that, I would like to give it to Angela, who is going to tell us a little bit more about how to improve performance and keep improving performance, given that now we have evaluation data.
All right, thanks everyone. Can you hear me?
No
Okay,
problem.
great. Okay, next slide. So when we think about improving performance, one of the things that we always go back to is like translation is ultimately like a user-facing technology. So when Paco opened, he talked a lot about kind of the natural use cases that we want to use translation for. And so when we think about what worldwide translation looks like this can inform a lot of our modeling decisions on like what kind of translation improvement and quality improvement we're looking for. So when we looked at this, I'm showing a diagram here where the color represents roughly like the number of requests in a translation direction, and the languages are listed along the X and the Y axis. So if we like zoom in on one of these things, each square represents a translation direction. And so the one that's shown here is French to Chinese, which is super relevant for me because I moved to France fairly recently, and like French to Chinese translation is something I use often. Next slide. And so if we reflect upon what worldwide translation actually looks like, you'll notice that like, you know, people are not just translating in and out of English, like Paco said, like there's a lot of translation demand through other different directions. And so basically everything here, you know, the fact that it's like, you know, a lot of different colors indicates that people have a lot of demand for translations through different languages besides English. Next slide. However, if you contrast, you know, the way people actually use translation in their daily lives and the translation research that the translation community does, you know, the research community more looks like this, where we focus on translation in and out of English. So for example, a lot of work on multilingual translation is done on data sets coming from the Workshop on Machine Translation, or WMT, and where these data sets kind of focus in and out of English. Same thing for a lot of publicly available data sets. And this has like, looks totally different from what actual translation demand looks like every day. Next slide. And so our main question of this section is like, you know, now that we have Flores, which supports, you know, this kind of many-to-many evaluation, how can we actually take multilingual translation as it exists today, which is very English-centric, into something that would support, you know, the kind of translation that we might want to use when we, you know, travel or talk to our grandparents and so on. Next slide. So the work that I want to talk about today is this work on beyond English-centric multilingual machine translation, which is done by a very large group of collaborators below. Next slide. So there's roughly 3 different schemes when we refer to multilingual translation. There's kind of 3 different schemes of how people do it. Now, the first is many-to-one, where we have many different input languages, for example, Chinese, French, Thai, and Nepali, and we want to translate into one, which is usually English. A second one is one-to-many, which is the reverse. And this work really wants to push into this true many-to-many direction, where the special spot that English plays is much more diminished, right? Like every single language is equal, and we're translating like between all of the different directions. And this is really what Flores also supports in terms of evaluation. Next slide. And so our, you know, what we're going to describe today is like what we actually model, which tries to bridge the gap between previous work, which is heavily English-centric, into what worldwide translation actually looks like. Next slide. And the major question is, well, if we want to do worldwide translation, then we want to cover, let's say, 100 languages. But how do we actually get 100 by 100 in one model? And I want to pause here real quick and kind of motivate why we want one model. And the main reason is that if you really want to go truly many-to-many, you know, it's going to be very, very challenging for us to build specialized bilingual systems. So let's say I want to cover like 10 directions in and out of English. This would only be like 20 models. And so, you know, it's slow, but I can imagine actually doing it. But if you want to scale to 100 by 100, if we want to go even beyond that, then it becomes really like limiting to try and train like specialized systems. And so that's where the kind of one model motivation solidly comes from. Next slide. So we have 2 challenges that we confront in this work, and the first is around data scarcity. Next slide. And first, when we think about training training translation models, as Paco described, it's a supervised training task. And so the major question is like, how do we actually get data to be able to support translating all of these languages? And so human translated training data is really scarce. Actually, if you look at a lot of the data distributed by the workshop on machine translation, a lot of that is not human translated, simply because it's so expensive and time consuming to get people to actually translate content naturally. And so what we use are large-scale data mining efforts called CC Aligned and CC Matrix, which are open source for everyone to use. So how does this work? The first step, which you see on the left, is you start with Common Crawl, which is an open source version of the web. And basically, this is kind of like content on the web, like when we browse Wikipedia every day. And the first step is that we actually extract all of the text from it, clean out all of the HTML, all of the noise, and then we try and find matching content that could be a translation. And the way this works is that all of the sentences are embedded into a multilingual embedding space, and then we calculate the distance between sentences in an embedding space, and when they're close, we find that this could be a translation. So obviously this is much noisier than actual human translation, right? Because there's no guarantee that the sentences exactly match, but we can get a much larger volume of content. And we found this to be empirically very successful. Next slide. And so how do we actually decide what languages to mine? 100 by 100, the intersection is a huge. So we actually prioritize mining in two different areas. The first is what we call bridge languages, which I show, in the upper left. And these are the major languages of the world. And you can think about kind of like your travel experience, right? Like when I first left China and went to America, Chinese, English, German, French, Japanese, these are kind of the major languages of the world, and they see tons of usage. And so we mine through every single major language of the world, languages that bridge different families. And that's why they're called bridge languages. The second is that we want to capture basically, language families that are commonly, spoken near each other and reflect kind of natural usage. So the one I have pulled up here is like Germanic languages. So you can think about in the Scandinavian regions, Sweden and Norway, there's a lot of translation between those languages that captures kind of, people's locales. Next slide. So now, how much data do we actually mine? So on the y-axis here, you have millions of sentences mined. And on the x-axis here, you have a bunch of different languages. So the gray color is data that we're able to mine through English. The orange is if we mine through the language family. So that's like mining Norwegian and Swedish. And the blue is mining through bridge languages. So for example, Hindi, Chinese, English, Japanese, and so on. And so the reflection point here is like, actually, if we mine through things that are not English, you get substantially more data, especially for other languages. And this is because, like when we translate between Spanish and French, for example, there's a lot of data here that you would not pick up if you're mining only through English. So not only is going beyond English-centric like a strong modeling motivation, but it actually provides a lot more data with which to train higher quality models. Next slide. And further beyond that, mining, it might not be able to take us all the way. So of course, there are many low resource directions where mining alone may not be sufficient. And so for these directions, we employ large scale back translation to be able to augment the amount of data available. Next slide. And so now let's pause here and we have this many-to-many data set that we've created. Like, how does it compare to going English-centric? So here, each row represents a baseline, and then we have 3 columns. The average of translation quality in blue score to English, then from English, and then all non-English directions. So that like French Chinese translation would fall under that 3rd column of non-English. So you can see the first row is bilingual baselines. If we train tons and tons and tons of different models and average them, this is the performance. And the second 2 rows are if I have an English-centric model, English-centric multilingual model, and then also if I do pivoting instead of zero-shot translation. Next slide. Now, what if we do like true many-to-many? So you can see that the performance to and from English actually doesn't suffer at all. There's a little minor variation in blue score, but it's largely within kind of natural variation. But on the non-English direction, you can see that it's substantially better. So if you compare many-to-many to row 2 English-centric, you're looking at an almost 10 blue point improvement, showing the power of many-to-many translation. Next slide. So that was on data scarcity. So now we tackle the second challenge, which is model capacity. Next slide. Okay, so what is the major challenge when we go from a bilingual model to a multilingual model? So in bilingual translation, we're working on languages. For example, I want to translate from the red language into the yellow language. So the encoder and the decoder, they only need to kind of learn one language each. But when we extend into the multilingual world, the challenge we have here is really like the encoder needs to represent 100 languages, the decoder needs to represent 100 languages, and somehow they need to learn some sort of relationship between all of these different languages, like that alignment on how you translate. And so this really strains the model capacity. Next slide. So a common way that you might think about tackling this is, well, let's scale up. And this is what model parallel, which is the type of basically scaling technique, allows us to do. And so, when people want to scale in transformers, they basically increase the width, increase the depth. Next slide. However, this comes with a lot of actual implementation-based challenges. So let's just reflect for a little bit. So the timeline we have here shows a bunch of different model sizes from 418 million parameters on the left all the way to 32 billion parameters on the right, which is like a very, very large model. And so how does this look in terms of compute? So on the left, we see that these models would actually fit on one GPU, but on the right, you see that the 32 billion parameter model is actually so large and needs 8 GPU just to hold it. Okay, next slide. But then how does this actually impact inference, right? We train the model on 8 GPU, sure, but how do we actually do inference? And actually, when you have a very, very large model like 32 billion parameters, you can't even do inference on one GPU. And so this, even though model parallel is a very exciting way to scale, it comes with this huge downside that we're not able to actually practically produce translations very quickly. So this is something to keep in mind. Next slide. However, let's talk about quality first. So the y-axis is BLEU score, and on the x-axis, we've grouped performance in terms of low resource languages, mid resource in the middle, and high resource on the right. And the colors indicate the different model sizes. So the lightest blue is around 11 billion parameters. So you can see that for low resource, actually improving the model size to 11 billion is not good because it begins to overfit and we don't have enough data. But for mid and high resource, model scaling does indeed improve performance. Next slide. And if you calculate across all languages the average, you'll see a pretty nice gap that you get when you scale the model size. So there is improved performance. Next slide. But the major question is, which is why I changed this to pause for reflection, is is this really worth it? So like I said, scaling model capacity does help with the challenge of representing 100 different languages. However, and we do see a BLEU improvement here. However, now we're talking about using tons of GPU to train, and we even need more than one GPU to produce translations, which means that ultimately we're producing a translation model that cannot really be practically used. Next slide. So now we want to consider alternatives to dense scaling. So the major problem with dense scaling is if I want to produce a translation now, every forward pass of the model, it activates all of these parameters, all of the width, all of the depth. And the question we confront next in the talk is really what is the alternative to this? Next slide. So we pursue a strategy called language-specific mixture of experts. And the idea here is we want a balance between shared and specialized capacity. So in this architecture diagram, the gray layers represent shared capacity that all of the languages are going to use. But then the little stacks of different colored layers represent specialized capacity. Next slide. And the idea is, instead of using the entirety of all of the parameters every single time you want to produce a translation, we're only going to activate a subset. So for example, we could activate the subset of blue parameters. Next slide. Or the subset of green parameters. Next slide. And so now when we're producing a translation from the red language into the yellow language, we'll hit the shared parameters that are gray, but then we'll activate the language specific parameters for the red and the same for the yellow. And so now for each language, we're activating a substantially smaller number of parameters. Next slide. And so there's three main advantages to this strategy. The first is that languages get dedicated capacity to specialize. So you don't have interference from trying to use one model for doing everything. But at the same time, we're able to train a very large model, but only using a single slice of it during inference, which means that we're able to train quickly and produce translations at a much more practical scale. And finally, this kind of sparsity is actually much more scalable. So you can have a much, much larger model if you scale through sparsity rather than scaling depths. Next slide. Now, let's talk about performance. So the first three rows here are the dense scaling that I talked about in the first part of the talk. And you can see the first column is the amount of parameters. So we go from 1 billion parameters to 12. And the second column is words per second. So that's like how fast that we're producing translations and training. And you can see the blue score in the remainder of the columns. And the major thing to notice is that going from 1 billion parameters to 12 billion parameters, you know, we have a 10x reduction in words per second. So we're training like, you know, substantially slower. Next slide. But now if we swap it and try and scale sparsely through these language specific parameters, we're still going from around 1 billion parameters to 10 billion parameters, but you'll see that the words per second, you know, it doesn't change very much. So we don't get that order of magnitude reduction. At the same time, actually, the performance has actually increased. And this indicates that sparse scaling is a much more practical strategy for, you know, sustainable development of large models, because we have better performance and much faster. Next slide. And further, you know, we can actually get improvement with language specific capacity. So the y-axis here is blue improvement compared to dense, right? So like, you know, anything positive is good. And you can see that because now each language gets its own dedicated capacity, you can have substantial increases in performance. So for example, Chinese to English gets the most improvement. And this is mainly because Chinese, you know, it has a lot of different characters, of course, similar to Japanese. So it needs a lot of capacity to be able to learn that. Next slide. So finally, you know, how do these models actually compare to models that people submit to, for example, WMT? So I list here like all of the different test sets that we evaluate on and their published results. Next slide. And now, like, how do we compare? So the major row we want to look at the major column we want to look at is the last column, which is the delta of improvement. On each row is a different language direction. So you'll see compared to like comparable models, we have about a 2 blue point improvement on average compared to all of these published results. I do want to note that these are comparable results. So submitting to WMT, many people are a fan of doing like multi-model ensembling, fine-tuning to the news domain. And so like we don't do any of that, mainly because it's not really scalable at our scale of like 100 by 100. And so we compare it to models that also don't do that. Next slide. And so a couple of concluding thoughts before we wrap up this part is that, you know, multilingual translation, it has a lot of potential, especially when you want to scale to true many-to-many, just because, you know, developing specialized bilingual models is very difficult at that scale. But further, you know, this challenge of how do we do multilingual translation with sufficient capacity is something that's ongoing, although we recommend sparse scaling as a very effective strategy. Next slide. Also, all of our code and models are open sourced at this link if you're interested in trying them out. Next slide. So we had a long talk about evaluation and modeling. Where might we go from here? I just want to kind of drop some open areas that people might be interested in looking into. Next slide. The first is tokenization. So when we want to build large-scale translation systems, how do we think about things like sentence tokenization or word tokenization? So languages like Thai, for example, they don't have like anything delimiting different sentences. There's no period, for example. And there are many languages where white space is not necessarily the way you want to tokenize. So how can we build translation systems that really extend to a variety of different languages? And beyond that, you know, is SPM enough? How do you balance languages in the vocabulary and so on? Next slide. I also want to think about evaluation beyond blue. So this entire talk, we've been talking about blue as if it's like, you know, the way to measure translation quality. But there's a lot of things that blue cannot measure. For example, gender bias. If you translate from a non-gendered language into a gendered language, there may be like critical factuality errors around named entities or others. And further, you know, if we want to go beyond sentence level translation into document level translation. And so these are a whole variety of different things that contribute to holistic translation quality that are really not captured in blue. Next slide. Also, data quantity continues to be a barrier. So there's a very few techniques that have been developed for low to no resource languages. So we talked about mining at the beginning of this part of the talk, but that really only works if there's a sufficient amount of monolingual data on the web. But there are a lot of languages where people are speaking them every day, but may not be typing in them. Maybe there's no even keyboard to support writing in that language. And further, these crawled multilingual data sets or mined multilingual data sets are incredibly noisy. There was this amazing data audit paper by Isaac that I've linked, for example, that indicates that even though we're using these systems to create a lot of data sets, a lot of them are not even in the right language. And this can be very detrimental to the quality of the models we produce. Next slide. And finally, I want to reflect a little bit on like, what does it mean to cover a language? So in multilingual translation, it's very popular, for example, to do 100 languages or more, like you hit that nice round number of 100. But what does it really mean to include a language? So many languages, it's like what people live and breathe every day. And so they have multiple different variants, multiple different dialects. Like I myself speak a variant of Chinese, that's not standard Mandarin. And so like, what does it mean to say like we translate Chinese perfectly? And so I think there's a whole space here of like adapting kind of standard translation into the translation that would be like, what your mom texts you every day. Next slide. And of course, tons more stuff. Thank you so much for listening to our talk. And Paco and I are happy to answer any questions.
Thank you very much for this talk. So now let's have a Q&A session. Please feel free to just unmute yourself and ask questions.
Can I have one question?
Yeah, please just go for it.
Okay. Hello, I'm Chanjun Park from Korea University in South Korea. First of all, thank you for such a great presentation. I have a question regarding SP Blue. A special token will be added when proceeding with sentence piece, I think, and this seemed to increase the blue score a lot. So are special tokens included when calculating blue scores, like underbar?
Yeah, so let me see if I got it. So when we are doing SP Blue, we are increasing the number of tokens, and hence we increase blue. Is that the question?
Yeah. So if we do proceed with sentence piece, there's adding a special token underbar. So I think it seems to increase the blue score. So our special token is included when calculating the blue scores.
I don't think we are including special tokens in this calculation, but let me actually revert it. Like, what is the importance of actually increasing the number of tokens, right? Think about languages that are relevant to this audience, like Burmese, like Thai, like Khmer, right? They don't have word boundaries. So if we use the standard blue, or even the ones that are using on top of Moses tokenizer, is not very useful for Asian languages. So this is why having SPM blue was really important, because now we can break into more meaningful units that are comparable. This, of course, this increases the blue score. But we in the paper, we do a full analysis and how does this relates with it correlates with human decisions, and we still find that SPM blue it does correlate well with human decisions, and it correlates with the standard blue as well. I don't know, Angela, do you want to add something here?
Yeah, I mean, in the end of the day, like the blue score is just a metric. Like, for example, like if you take a question answering data set, the accuracy, if I throw in a couple easy questions, then your accuracy will magically improve. But at the end of the day, it's just a metric. So it's all about relative improvement. Like a blue score of 20, it doesn't really, mean anything. And so it's similarly, like if we increase it to 22, it similarly also does not mean anything, right? It's just about like, how much are we improving, and also how does it align with human quality? So those are the major questions that we investigated in the work to decide, should we go with SP Blue or not?
Thank you.
Thank you very much for the very valuable presentation. I would like to know when my practical experience when I trained the M2M model. So I couldn't train on the full GPU. So how can I train my model in the fit to the full GPUs?
Yeah, we understand fully that like scaling is kind of like, not a very practical usage of translation, right? Like translation in the end of the day, like we're supposed to be delivering translations. So a lot of the, questions are around like the practicality of translation. So when we open source our model, we open sourced actually five different sizes of our model so that you don't necessarily need 4 GPU to train. So we do open source our largest and highest quality models so that people can reproduce our results. But then we also open source 4 models that can fit on a variety of different sizes of GPU. So there's also different generations of GPU. So our 1 billion parameter model, for example, I think can only fit on a V100, but our smallest model, which is only a 135 million parameters, can fit on like an M40 or like a K40. And so you can download those from the Flores website. And so that gives you like a variety of different sizes for which to begin like fine tuning or experimenting with. And yeah, it just provides a more variety for people.
Thank you.
I have a couple of questions. So regarding the Flores 101 dataset, currently is the dataset at a document level or is it just at the sentence level? Because at some point of time, we would like to do document level evaluation. So just want to know if there are any already the meta tags or the document level tags are already available or not.
Yeah, so the document level tags are there. So if you look at open the data set, it does include the URL from which this was sourced, and that serves as an identifier for the document.
Awesome. That's awesome. So then the next question is, what are the plans? Like I know you talked about dialects. Dialectical evaluation would be one of the next major steps. So are there any plans, or are you guys already planning towards this, or what's the direction that's going to take?
Paco, you should answer this one. Paco has a lot of passion on this area. I have to toss it to him.
Yeah, so there are plans around dialects. This is something that we care a lot about, especially for languages for which the notion of language is very fluid, right? Think about Arabic, right? But also think about major languages, variations of French, right? In Africa, for example, or Latin American Spanish could be very different from. So this is something that we are actively looking at. I don't have a timeline to tell you when exactly Flores dialects will come out, but this is something that we are actively looking at, and expanding, of course, Flores 101 is something that we are looking in the future.
That's really cool, because even in India, although we say the major languages be Marathi, Hindi, or what have you, most of the time it's dialects. Even when I'm back at my home, I speak in a dialect of Marathi and not the pure Marathi per se. So I think that would be the way we could connect more with the actual people who are going to use these products. So that's definitely going to be fun. Okay, awesome. That's one thing. If anybody has any questions, please feel free to stop me, because I have some quite a few other questions. So what's your take on language family specific models versus having one single global model for everything? Because as in your talk, it's very clear that there are clusters of languages where the activity of translation becomes more and more important. So I don't expect someone who speaks Hindi to want to probably translate into Yoruba or something. So usually Indian people, if they have any translation requirements, most of them will have translation requirements either to English, to some of the major languages, or mostly within India. So what's your take on, do we really need to go for those 6,000 languages in one single model? Or should we focus on language clusters and then have many models in those clusters?
Yeah, great question. So actually, even though we mine data, we don't mine through all of those different languages, exactly as you said, like, the demand for Marathi into Icelandic translation, let's just say it's very low. So we only have supervised data through like language family clusters, or like major languages to cover like kind of travel use cases, or like if I want to read, like a Chinese newspaper or something like that, precisely for those reasons you described. We did experiment with kind of language family related models. So one of the things we spent a lot of time on was like Slavic language family, like 11 different Slavic languages. And you do see a lot of performance gain because, they specialize in Cyrillic, basically, for example. But, going beyond that, the notion of language family, it doesn't often correlate with performance. So for example, a lot of people group like tons of African languages together, or like many Indian languages together. But like if you have Indian languages and like many different script, they don't group together very well. And so actually you lose performance. And so, yeah, it's definitely something to consider. And then for our kind of scaling strategy, one of those reasons why we wanted to scale through languages or language family clusters is that it does allow like languages where they talk about similar content to overlap a little bit more naturally. Although there are now a mixture of expert strategies where they don't kind of hard code in language family information, but they allow the model to learn. And interestingly, a lot of those patterns, they kind of recover, natural language family groupings, like precisely for the reasons that you've described.
Awesome. Yeah. So then my final question is, so now that you have these huge models, have you experimented with distillation or maybe with pruning approaches? Because that's probably the most straightforward approach to get rid of like 90% of your parameters and still, retain performance mostly. So any thoughts on that?
Yes, so one of the things I focused a lot on before I worked on translation was around quantization, basically putting models on device. So yeah, if anyone is interested, come to the Sustainable NLP workshop at EMNLP that I'm organizing. Yeah, so we're very interested in things like distillation, pruning-based approaches, and also like very heavy quantization, exactly to make those models smaller. And one of the reasons why we release like so many different sizes of models is as well to let people kind of explore. So different distillation techniques work differently on different sizes of like teacher model and things like that. So yes, we're very, very interested in this direction.
Okay, awesome. I think that's all the questions I have. Thank you very much for that. Does anyone else have any other questions? We still have.
Yes, may I have one?
Yeah.
Sorry.
Hello.
Yeah, please go ahead.
This is Jay from NECTEC, Thailand. I have one question. Did you make some cleaning on the noisy data? So what I understand from your presentation, if I'm not wrong, I think you did some mining to get a parallel data. So for example, like Burmese or Myanmar language, we have kind of generally two different encoding systems. Still, in particularly on the WAT, they are messy together. And let's say if I mine, we have to do a lot of critical cleaning. So I guess for some under-resourced languages, that kind of problem, similar problem might happen. So if you did some kind of cleaning or kind of normalization on the minor data, let me hear.
Yeah, that's a problem we face literally all the time. So actually in our open source repository where I linked it, we have also open sourced our pre-processing scripts, the cleaning scripts. So we apply a lot of like general cleaning techniques like language identification, for example, removing noisy sentences where the source and the target are mismatched and so on. But we also completely agree that many languages require language specific cleaning. So for example, Chinese, if you mine, you get both traditional and simplified Chinese, but the test data set is often only in one of them. So like mining both of them is not useful. And this is very challenging because different languages, it requires like knowledge of each language in order to understand where these problems may arise. And so in the original release, we tried, but it's not perfect. And so this is something that we're working with a lot of linguists on who speak many of these different languages and have a network of different people who can kind of inform. And so we're noticing like a lot of these things and also want to improve. And we do want to also open source these types of cleaning strategies in the future. And one of the things we noticed for Thai, for example, is our sentence segmentation for Thai is like very poor. So we're not necessarily mining like sentences as much as like general phrases that are like roughly sentence length. So those are the things that we've noticed, and we're definitely looking to improve them.
And just one thing, I mean, things that we noticed, for example, with Burmese, Sauji and Unicode, and there's a lot of confusion and not a real mapping. So this is where having people, everything that we're doing, we're open sourcing, right? And the repositories are there. So if you have contributions that you want to make, please let us know, right? And actually, I just wanted to take this opportunity to invite the WAT community to keep using Flores, right? Right now, it's covering a lot of languages. So this is a challenging data set, and we are not releasing the test partitions. We're at the moment, we're still running a multilingual task, shared task, but inviting you to take some of those languages and run a shared task on the languages that you care about. I think this is something that we totally encourage you. And if you have improvements on pre-processing and things that we can incorporate into mining, etc., we're open to collaboration. So do let us know.
Yeah, thank you. One more thing is that previous questioner mentioned. Actually, the evaluation with Blue Score is also we already know we need to improve in some way. So that's why like CRF CHR CHRF plus I think a kind of modified Blue Score evaluation also occurred. So what I mean is the segmentation land, the unit, a number of unit, and the evaluation are kind of related. And in particularly, if we right now for the NMT, we are mainly using the sub unit or sub-watt unit. So that is kind of solving in some way, but if we use the sub-watt unit, the Blue Score is getting higher. So that is also a kind of uh, especially if we want to measure between two watt unit languages to want to see kind of relationship or the machine translation performance. Sometimes it's really ambiguous result happen. I think especially if we work with noisy data, so it's difficult to manage well. So just my comment. And if you have anything, please. Yeah.
Yes,
Thank you.
I thank you so much for your comment. I think I totally agree. It's changing the segmentation makes things non-comparable, but this is why we're working with Sacre Blue. So to generate this model, and it becomes a kind of like a fingerprint. So now when you're reporting blues, you report SPM blue as computed by Sacre Blue. So it's not going to be, so we know that these results are comparable across them, right? And the other thing is, once we have this SPM blue out, we know that it's not perfect, but at least it's a conversation starter. If you come later and say, now with my pre-processing scripts, we can create a better SPM blue, then that opens a line of research, right? So I think it's not perfect, and it's something we can improve on. And if you have suggestions, I totally encourage you to work on that.
Thank you. Thank you. It's a big deal. Yeah.
Okay, so I'd like to bring a close to this invited talk because we are running a little bit behind schedule. So thank you very much, Paco and Angela. So if there are people who have questions, you can directly approach Paco and Angela via chat, and then maybe they can answer your questions. But yes, thank you very much for this very informative talk. And we really hope that this kind of Flores evaluation definitely gets adopted more and more. So with that, this invited talk session is done, and let's move on. Nakazawa-san, would you like to take over?
Yeah, okay. Thank you very much, Paco and Angela. It's very interesting talk. And yeah, let's start the next session from in few minutes, maybe. And yeah, Akiko Eriguchi-san will start the next session.
Okay.
Are you ready? Yeah.
Yeah. Can I try to screen my presentation?
Yeah. Please. Yes, please. Yeah, we can see the slides now. Okay, so we are actually behind the schedule. If you are ready, please start the next session. And the next session is the shared task 1, restricted translations and ART plus UCSY and NSET SAP. And starting from the Eriguchi-san's talk.
Yeah, just want to confirm that does anyone wants to try the presentation? or like, can I just start from now on, because like we have two speakers like after my presentation. So I just wonder, like, is everyone okay?
I hope so.
Okay, so let me share my screen then.
Yeah, the screen is shared already.
Do you see my PowerPoint or?
Yeah, but it's not the first screen. It's we can see the presentation mode.
Okay.
Present part.
That's also. Let me try again. Sure. Okay. Let's see.
Yeah, no, it's fine. Yeah.
Okay. Yeah, so
Uh,
yeah, do you mind if I just go down like with this slide, or do you see my screen?
yeah. Okay, I think it's okay.
Okay, yeah, thank you. Yeah, so hi everyone, I'm Akiko, the one of the task organizers of the restricted translation task. And today I'm going to talk about why and how we designed this kind of the empty task. And we're gonna briefly touch the final results, including the human evaluation. And despite of the brand new empty task to the WAT 2021, so we received a couple of submitted systems, and thank you for your interest and participants. Okay. Right, so when we use empty systems, so we often notice that each empty system has some preferences, like in terminology when translation. So in the following examples, the different online systems translate a scientific text from ASPEC corpus from Japanese to English. And we observe that the red color technical term, that is the magnetic features, like in the reference data, got translated differently in each online systems. And this type of issues like would cause some headaches in practical scenarios when using the empty systems. And especially in the documented about translation, we often expect the systems to give translation outputs with consistent terminology regarding technical terms, proper nouns in the entire document. So to tackle this type of consistency issue, we have extended ASPEC translation task, which is a popular empty task at WAT, containing lots of the scientific terminology, and designed a restricted translation task. In the task, we ask participants to build systems that translate sentences with a target vocabulary list that we provided in advance. So in other words, the translation outputs must contain all the word or the phrases listed in the provided vocabulary. The vocabulary list contains the scientific terms in the target language. For simplicity, we do not accept other terms that are semantically similar to the specified ones. So in the following figures, we will penalize the magnetic characteristics because of not being in the restricted vocabulary list. And next, we started the building such restricted vocabularies from ASPEC Copper. We employed 10 bilingual speakers in English and Japanese and asked them to annotate technical terms, phrases as much as possible. We observed that each sentence contains approximately 3 phrases, like as a technical terms. And after creating the corresponding restricted vocabularies to all the ASPEC evaluation data, including the DEB and DEB test and the test set for both English to Japanese and Japanese to English directions, we provided these vocabulary files to the participants as the vocabulary constraints. And to appraise systems from the consistent aware perspective, we also designed a task-specific automatic evaluation metric. To get the final ranking, we employed two different metrics: BREW score to measure translation accuracy as usual, and exact match score with restricted vocabulary to measure consistency in the translation output. As we discussed already, so we are going to penalize the first translation candidate because the phrase magnetic characteristics doesn't satisfy the vocabulary constraints. Overall, we received the 7 systems, 3 systems submitted for English to Japanese task and 4 systems for Japanese English to task this year. Since we have participants' presentation right after these task overviews, I would like to leave the details of the submitted systems to the speakers. But we found that the major approaches of the task are how to deal lexical constraints and decoding with the neural MT systems. And this topic is quite exciting. Okay, so let's take our deep dive into the results quickly. So the right table reports the final score and the human evaluation result that we conducted. So as a human evaluation, we employed a source-based direct assessment and the constructive assessment. And we sorted the submitted systems based on the final rank first. And first of all, I'd like to note that our design evaluation metric is well correlated with the human evaluation scores. And the top ranked team, NTT, in the both tasks, won the best human results, evaluation results too, and congratulations. And surprisingly, we found that some of the systems in this task are even higher than the human references in the human evaluation campaign. So does that mean do the systems achieve the human parity in this task? So maybe yes and maybe not, because we analyzed the human reference data very carefully, and we detected there are low quality human reference data with around the 12% or 13% ratio. And we might want to clean the ASPEC evaluation sets probably next year. Okay, so we present what restricted translation task look like briefly. And the restricted translation task is how to translate sentences with given target vocabulary constraints. And for this purpose, we built a restricted vocabulary from ASPEC corpus and also designed the task-specific evaluation metric. And we discussed how the MT systems can achieve the consistent translation given this type of the constraints. And as a result, the team NTT got 1 in both English-Japanese and Japanese-to-English tasks, which human eval results also supported, we confirmed. Yeah, that's all from my side, and thank you for listening.
Okay, thank you. Maybe the next will be the ALT plus UCSY task, but I think the presenter is not here yet. So Raj, could you start the next one?
Yeah. Let me just give a quick overview of the NICT SAP task. Just a moment. This one. So I'll give a quick overview of the NICT SAP shared task. This shared task is actually the same as the shared task we said last year, but unfortunately last year we had only one participant, which was basically me. This task covers 4 low resource languages: Hindi, Thai, Malay, and Indonesian. And when I say low resource, I'm talking about domains. There are 2 domains we are evaluating on. One is software documentation, which is the IT domain, and the evaluation data was created by SAP. On the other hand, we also evaluate on the Wikinews domain coming from the Asian language tree bank data set. Both have very low amounts of training data. And the constraints of this task is that we prefer multilingual solutions, and people were allowed to use any monolingual or parallel corpora as long as they did not overlap with the evaluation data. So some quick findings: we had 5 participants and 3 system description papers. I didn't expect that people would actually participate, given that nobody participated last year. So it was pretty nice. We had papers by Bering Lab, Sakura, and NICT2. Although one of the teams called JB4 got good scores, they didn't submit a paper. And Bering Lab got highest blue in a number of cases, but for some reason, we didn't find that they submitted for human evaluation. The types of solutions we observed were ones which use data selection, pre-training and fine-tuning, and multilingualism. And the main observations were that we get large gains of 14 to 30 blue over organizers baseline, which organizers baseline is a very naive bilingual baseline trained on parallel corpora that were available from Opus. The other observation is that pre-training really helps, which really contributes towards the large improvements. And perhaps the fact that we get large improvements on the evaluation data means that evaluation data was probably too easy. Maybe we need harder evaluation data for these domains. As for human evaluation, we could only do human evaluation for English to Indonesian and English to Malay for the software documentation dataset. And the 2 top teams in human evaluation and blue were Sakura and NICT2. Although, as I mentioned, that Bering Lab also had the highest performance in a number of cases. So you can see that most of the translations, according to human evaluation, are in the range of perfect translations or almost perfect translations. So it means that whatever approaches were employed do satisfy the translation requirements in a number of cases. This is for English to Indonesian, and this is for English to Malay. And you can see that, yeah, the performance is pretty good regarding whatever has been submitted. So yeah, there's almost an equal proportion of 5, 4, and 3 scored sentences, which means we're getting good quality. And the blue gaps, the blue improvements do correlate with human evaluation. We did observe gaps between human scores of 0.08 and 0.15 for the top 2 performing teams, which is not particularly large, which probably means that although there is a difference in blue of 1 to 2, these 2 systems may not actually be that different in practice. This needs more investigation, of course. The next step is probably do some document level evaluation, because the evaluation data are at document level. But how to evaluate document level machine translation is a good question. So we might have to think about it. And maybe we should work on getting cleaner training data, because the existing data is pretty small and maybe is not that very perfect. So that's the overview of this particular task. And let's move on to the shared task paper presentations. Nakazawa-san, who's the chair for this session?
Actually, the task organizer will chair the
Okay,
session.
okay.
Yeah. So,
Okay,
yeah.
Next is me.
Let me see. Who will next?
Next will be the NHK team.
Okay. So is there Minasan? Or...
Yes. Can you hear me?
Yes, we can hear you.
Share the screen. Can you see the slides?
Yes. If you're ready, like start. Okay. So sorry, like I need to introduce. So yeah, we have the three the system description papers, like the attended in the restricted translation task, and the first speakers from that like is Mino-san, like from NHK, and the title is the NHK Soft Rex Career Constraint in Neural Machine Translation at WAT 2021.
Thank you. I'm Hideo Mino from NHK and Tokyo Institute of Technologies, and I'll talk about NHK's lexically constrained neural machine translation at WAT 2021. And I skip this slide because the organizers already explained the details of this task. So I show you about the approaches to deal with this task. Maybe there are two approaches to deal this restricted translation task. The first approach is to train with constraint. This method integrates the constraints during training. And the merit of this method is no need to modify the model, and there's no use of any other resources like a dictionary. However, the merit of this method is not guaranteed to be appear as a constraint in the translation output. And secondly, for the other directions, there is a beam search decoding with constraints, and maybe it's a major approach. And this method modifies the decoding step to satisfy the constraints. And the merit of this method can control the enforcement of constraints. And the demerit of this method is high computational cost, and some papers shows the degradation of the translation quality due to the strict enforcement of the constraints. And in this paper, we use the first approach, training with constraints. And let me show the model of the method, the first approach. The above one is a vanilla NMT, as you know. So it means that the input is the only source sentence, and NMT outputs the translation output. And for the other method, the lexically constrained NMT, as shown in IJCAI, in addition to source sentence constraints, the word list is attached to with the source sentence for input, and NMT outputs the translation output. And of course we use the bottom model. And the feature of this model is for the training and translation phases, we need to prepare the constraint. And in this task, for translation phase, constraints are given by organizers. However, for training data, there are no constraints. So we have to extract constraints from training data by any method and by any means. So how should we get constraints for training? A related work of Chen extracted constraints randomly from target sentence on training data. So this is an example of the extraction randomly. Public opinion will favor it. From the sentence, the candidate of constraint is public opinion will favor it, and dot. But maybe this random extraction of the related work is not appropriate for this task. So we use the other extraction of constraints. We can use the task description. In the task description, it is practically important to have consistent terminology when translating documents related to science or business marketing that include technical terms and proper nouns. This is a clue for extraction. So anyway, in this paper, we proposed effective ways to extract constraints for this task. This is a proposed method with two types of constraint. The first is proper noun constraint, as I said before, as the present slide from the clue of the task description. We suppose that the important words such as technical terms and proper noun tend to be selected as constraints. So we extracted proper nouns on the basis of the named entity recognition, NER. And in this method, public opinion is extracted. And second method is a mistranslated word constraint. For this method, we extracted mistranslated or dropped word by a vanilla NMT. The procedure is as below. So first, we trained the NMT model on parallel training data, and then we translated the source sentences, all source sentences in training data with this vanilla NMT model. And then we picked out the words does not appear in the translated sentence, but appear in the target sentence. In this method, a favor is extracted. And the third method is both proper noun and mistranslated word constraint, both of them. Then we move to the experiments. System setup. For training data, we use only the first two mega data in the full training data of ASPEC. And then we use NMT. We use transformer as NMT. And for NER, we use Ginza and Spacey. And for baseline systems, we use vanilla NMT, which doesn't use any constraint information. And for the second baseline systems, we use random lexically constrained NMT as change shows. And for evaluation criteria, we use blue and consistency rate as organizers used. And this is the results. Compared with the baseline system, our proposed method improves both consistency rates and blue scores. And in the proposed method, three of them, the systems used both of them the highest accuracy and blue score. And though models using the random method related work can improve the consistency rate compared with the vanilla NMT. However, there's no little improvement in blue score. And this is the conclusion. We propose a way to extract constraints to train the lexical constraint NMT. And experiment results shows the effectiveness of our proposed method. And for future work, we want to use the Moninger data for the data augmentation, and we have to tune the hyperparameters. And of course, we want to compare the proposed method with the other state-of-the-art methods, which is other participants' work. Thank you for your attention.
All right, thank you for the presentation, Mino-san. So we seem to be a bit behind the schedule, so shall we move on the next speakers? And
yes.
I think the Raji suggesting us that why don't we have creating the breakout rooms for the question Q&A session later. So all right, the next speaker is is Katsuki. I think there is.
Yes.
Is there speakers? Okay. Can you try to share screen?
Okay.
Let me just interrupt quickly. I have created a breakout room for each talk. So in case you have any Q&A please ask in the breakout room.
Sounds great. Thank you, Raji. Okay, so the next speaker is Katsuki, and so the title is the input augmentation improves constrained beam search for neural machine translation NDT at WAT 2021.
Okay, can you see my presentation? Can you hear me?
Yes.
Okay. Yeah, thank you for introduction. I'm Katsuki Chosa from NTT Communication Science Laboratories. I'm delighted to talk about the overview of our system for the restricted translation task. This is a joint work with my colleague Makoto Morishita. In this task, the translations that do not satisfy the constraints lead to a substantial decrease of the final score in the evaluation. Therefore, the system is required to generate translations that contain all the constraints. So there are some previous works for constraint MT, and these methods can be divided into two categories, soft and hard constraint. Soft constraint method does not guarantee satisfying constraints. These methods usually modify the input of an MT with constraint information, and the success rate of generating constraint is about 70 to 95%. Another method is hard constraint method, which guarantees satisfying constraint. They usually use split beam search as decoding algorithm, as known as lexically constrained decoding, LCD. The beam size and inference time increases according to increase the number of tokens of constraints. Since satisfying constraints is necessary in this task, we first adopted lexically constrained decoding, LCD. To evaluate the performance of LCD, we compare the baseline and the baseline with LCD on Japanese to English translation task. Here, the baseline model is transformative, and we use two metrics for the consistency score, term percent and cent percent. Term percent is the ratio of completely generated constraints, and cent percent is the ratio of sentences satisfying constraints. This table shows that LCD significantly improves the consistency scores. Term percent and cent percent are not 100% due to normalization issues, but constraints are completely generated, and this problem can be addressed by post-processing. We found that to successfully generate all constraints, the beam size K needs to be larger than 60. We also found that baseline plus LCD decreased the translation accuracy on Japanese to English translation. It is because some translations contain much repetition, and the model never finished generation before reaching the maximum output length. This repetition mainly happens after the model finished translating source sentences without using constraints. This is a translation example. Obviously, base plus LCD generated semantically similar phrases to the constraint superconductivity single-phase auto-transformer in the early time step, and the same term repeatedly until generating all the constraints. One likely reason for this is transformer cannot use constraint information to predict token probabilities and cannot properly decide where to output constraints. To ease this problem, we also introduced lexically constraint aware NMT called LECA, proposed by Chen at IGCAI, IGCAI 20. This is one of the soft constraint methods whose input is concatenating a source sentence and constraint, as shown in this figure. This method can inform the model of what constraints are given before decoding time, and so the model may be able to properly decide where to output constraints. Moreover, in combination with LCD, we can guarantee the model satisfying constraints. We evaluated the performance of Leka with the same settings of the previous experiments. This table shows that Leka achieves high translation accuracy and consistency scores without LCD. It achieves plus 18.2 in blue, even though the input of Leka and baseline plus LCD are same. These results imply that inputting both a source sentence and constraint is very effective for improving the performance in this task. However, Leka does not satisfy all constraints. In combination with LCD, it can satisfy all constraints and improve blue score with half of the baseline beam size. Revisiting the example, in contrast to base plus LCD, Leka plus LCD successfully translated with all the constraints. We believe this is because Leka correctly gives higher probabilities, higher scores to the constraint tokens at appropriate time steps. Finally, this is an overview of our system. Our system combines lexically constrained beam search and input augmentation. For training data, we create synthetic corpus from noisy data. Based on the previous work analysis, we forward translated for Japanese to English and back translated it for English to Japanese data of aspect. We also applied a model ensembling technique. We trained 8 models with defined random seeds and average scores of these models. This is translation accuracy results of our system measured in the evaluation server. As you can see, Leka, LCD, and ensembling improves the blue scores for both directions. The best systems significantly improved the blue score by plus 11.93 for English to Japanese and plus 15.04 for Japanese to English against baseline model. And this is official results of our best systems. Our system achieved the best scores in the final ranking. Our final scores are not dropped from the blue. This means our system succeeded in generating all given constraints perfectly. Our system also achieved the best in human evaluations, and our scores are better than the reference one, even for Japanese to English. This implies constrained MT might be able to yield human parity performance when appropriate constraints are selected. In addition, we analyzed how can Leka plus LCD reduce the beam size. This figure shows the blue scores on English to Japanese translation, recording with various beam sizes. As already mentioned, baseline plus LCD needs the beam size to be larger than 60 to successfully generate all constraints. In contrast to this, Leka plus LCD can satisfy the constraints and improve the translation accuracy even when the beam size is set to 5. This is the practical setting. This result indicates that the output of Leka is helpful for LCD to score the candidate in beam, and Leka can save inference time. In conclusion, our system combines input augmentation and constraint beam search algorithm. Through the experiment, we found that input augmentation makes constraint beam search more effective. We also found that combining these methods significantly improves translation accuracy and save the inference time. As a future work, it is remained to consider the method that automatically obtains appropriate constraint terms. This is the end of my presentation. Thank you.
Thank you, Katsuki. This is great work. Okay, shall we move on to the next speakers? I think the next speaker will be the to show lead, like the title is NICT's Neural Machine Translation Systems for the WAT21 Restricted Translation Task. Okay, yeah,
Okay.
we can see the screen.
Could you hear me?
Yes.
Okay, thank you. Today I will share my recent work in the WT21 Restrict Translation Task. It comes from the NCT and CGTU. So in this work, we tried two methods. The first is restrict translation training. We proposed sampled constraints as concentration loss. And the second is the commonly used lexically constraint decoding. We employ two baselines. The first is transformer MT model. The second is sparse transformer MT model. So this is an example. If we give an input and we enforce these constraints in the translation, so we need to generate this constraint in the translations. So in the first, we shared my sampled constraints as constraint training. First, in this model, if we take the probability form, we think we add the constraint C in the as additional input for the probability form. So I employed the self-tension in the decoder to encoding these constraints without position encoding and with bidirectional attention. Then we used this additional context. We employed two cross attention to query first query the source at representation. First, second query the constraint representation. Then in the training, because we don't have the constraints, so we sampled the target and as an additional context. Then we add a penalty on these constraints because we asked these leaked clues to be more accurate in the translation. So that is a model illustration. So this is a training procedure. First, if in the model, we use the encoder to encode the source input, and then we can use the decoder to query, to do self-attention and cross-attention on the source context. Then we use two procedures, sub-procedures. First is end-to-end translation. It calculates the loss as a normal translation model. But with the second, we use in the restricted translation training, we sample the target and we use the self-tension in the decoder to encoding these constraints, and then do two-pass cross-attention to get the final loss. So the second is the lexical constraint decoding, because it is a commonly employed approach for enforced the given constraints sequence to appear in the generated sequence. So this is the first baseline. In the normally transformer, we use multi-attention to calculate the representation. But in the sparse transformer, we need to do some extract some local context. So we use a deep convolution to do the encoding process. So I implement my work in the field circle toolkit. We do a 40K joint match operations in the fast BPE, and we use this training data to pre-training the MT model and then fine-tune the ISPC data. So we use two objectives. The first is cross entropy with label smoothing of 0.1, and the second is data dependent Gaussian prior objective. This is the official evaluator results. We can say from the results, our model with the sampled constraint training and the constraint decoding, we can improve the baseline. And if we do the ensemble on these two different baselines, we see a further improvement. This is a further exploration on this data set because we when we compare the end-to-end translation baseline and the only the constraint decoding, we say the Brew is much improved, and the exact match of the constraints also improves in a large margin. So, but if and in our the constraint as a constant context only training, we say our Brew also gets improved, but compared with the constraint decoding, it's not, because it is a soft constraint, so the score is not so high. So we integrate the two kinds of methods, we get better results. So from the right figure, we compare the Brew versus beam search and the time with different beam size. When we say in the constraint decoding, the beam size is get larger, the results get better. But in the normal translation, the beam size can be smaller. And from that right figure, when we enlarge the beam size, the time gets much higher. So it is very the computational expensive. We also conduct experiments on the English to German and English to French. We say when we sampled some constraints, we can say the Brew gets much improved. The round 1, round 2, and round 3 and round 4 means we randomly sampled 1, 2, 3, 4 tokens from the target as the constraint in the test set. And the phrase 4 means we sampled continuous tokens from the test set. So it means when we enforce the constraints, the score and the translation performance will be much improved. Okay, that's all. Thank you.
Thank you, Zhou. Nice analysis, which is quite helpful. All right. Let me see. All right, we have the next speaker, Seiichiro Kondo. The title is The Machine Translation with the Pre-Specified Target Side Words Using a Semi-Autoregressive Model.
Can you hear me?
Yes, and we can see your screen.
Thank you. Hello everyone. I am Seiichiro Kondo from Tokyo Metropolitan University. We explain about TMU Japanese to English system, which employs a semi-autoregressive model to tackle the WAT 2021 restricted translation task. In the beginning, I'd like to give a brief overview of restricted translation task. This task requires the output sentence to contain all the pre-specified restricted target vocabularies, which is called RTVs. We are given a source sentence and a set of RTVs, and we are supposed to generate an output sentence that contains all of them. Note that each RTV is either a word or phrase. We tackle this task as follows. First, we defined corpus refinement by word translation. Secondly, we use recover-stat to insert RTVs. Additionally, we decide the order of inserting RTVs by using source alignment. First, I explain about corpus refinement. In this study, we used aspect dataset. The training sentence of this dataset were ordered by sentence alignment scores, and so the sentences with lower scores were considered relatively noisy data. Therefore, we refined the latter half of the training data by word translation following Morris et al. We first trained the Japanese to English translation model on the first half of the aspect training data. And subsequently, we used the model to translate the latter half of the Japanese sentences in the aspect training data and obtained refined English sentences. Finally, we combined the first half of the training data and the refined sentences for the new training data. Next, I explain about the architecture of recover-stat proposed by Lan et al. Recoversat is a semi-autoregressive model that performs generation autoregressively in local and non-autoregressively in global. At each decoding step, the model generates a token in each segment, with paying attention to not only all the previous tokens in the segment, but also those in all the other segments. The model continues decoding in each segment until either special token, EOS or DL, is generated, or the length of the generated token reaches a maximum token number. The final translation is a concatenation of the segments, except those that end with DL. Now et al. Manually forced the model to generate a certain token in their case study. They called forced translation. We took advantage of it to generate the RTBs in the output sentences. In this approach, the model generates the RTBs at the beginning of an arbitrary segment. Once the RTBs has been generated, the model predicts the remainder of the segment in an autoregressive manner. In contrast to the original forced translation, which only takes one constraint word, we are required to place multiple RTBs in a translation. To compensate for this gap, we place the RTBs at this equation. When the RTBs have more places than segments during inference, we cut off places in the RTBs from the tape to fit the placeholder. Finally, I explain sorting RTBs using source alignment. Recoversat outputs RTBs in the order where they are inserted, so the order of inserting RTBs is important for accurate translation. We determine the order under the assumption that it correlated with the order of the alignment words in the input sentence. We used Visa++ to align each RTB with a word in input sentence and sorted RTBs in the order their corresponding input words. Experimental setup. We use the aspect dataset for Japanese to English translation. As I mentioned before, we define the latter half of the training data using for translation. We use the sentence piece to tokenize the training data. When determining the insertion order of RTBs using Visa++, we used Makeup with IPADIC to tokenize Japanese sentences. We use a transformer-based model for forward translation and Recoversat for main task. We examine the four models with different numbers of segments. We evaluate system outputs using two distinct metrics, blue score and consistency score. The consistency score is a ratio of translations that satisfy the exact match of all the given constraints over the entire test corpus. We simply lowercase hypotheses and RTBs, and then judge the character levels against matching, including white spaces. This is the result. The number of segments of RTB, the number of segments of Recoversat is 10. The meaning of each line is as shown below the table. It shows that Recoversat with forced translation outputs RTBs in almost all the cases. Also, sorting the RTBs using Visa++ improves the blue score. However, there is still significant gap in the scores compared with those obtained using the Oracle order. This is because the word order between Japanese and English is different. The figure shows the blue scores for different number of segments. It shows that the translation accuracy decreases as the number of segments increases, similar to the previous study. This may be because the model predicts the target token more independently as the number of segments increases. Also, when the number of segments was 10, we could not insert all the RTBs in some test sentences with more than 10 RTBs. On the other hand, when the number of the segments was 14 or more, we could insert all the RTVs. However, the final root score of 10 segments is the highest. This is an example. The yellow underlined phrases are RTVs. Tau means candle rank correlation coefficient of RTVs. And with sorting is the output result of the model we submitted. Conclusions: we introduced the semi-autoregressive approach to tackle the restricted translation task. In our experiments, we showed that a recover set with forced translation could output almost all the RTVs. Moreover, the importance of the order of the RTVs was confirmed by the fact that the scores was considerably improved by inserting RTVs in order in which they appear in the reference translations. In future work, investigating how to determine the best order to insert RTVs will be necessary. Thank you for listening.
Thank you. Let me see. Yeah, thank you, Seichiro, for the nice separation study work. Okay, so who will be the next? Okay, so the next speaker is the Fung. Sorry, like for my bad pronunciation, but so the paper title is the NACTC's participation in WAT 2021.
Hello, can you hear me?
Yes, we can hear you.
Can you see my slide?
Yes, please go ahead.
Hello, everyone. My name is Salai. I'm a PhD student from Kim Mong-Go Institute of Technology, Bangkok. Today, I would like to present the research topics and title, latest participation in WAT 2021. These are the outlines of this presentation. This is the first time participation in WAT 2021 as a nested team, and I'd like to introduce my research work. NN3 has become the state-of-the-art approach compared to previous SMT approach. The ACT NN3 models do not write use synthetic information, and thus we propose tree-to-string and POI-to-string NNT system by multi-source translation models. To the best of our knowledge, no experiments have been conducted for multi-source NNT system using POS data and synthetic tree information. In particular, multi-source NNT system had not been established in Myanmar language, and thus we implemented a multi-source NNT system for Myanmar to English and English to Myanmar translation. To read NNT models, we use Mayan frameworks with transformers and INFs encoder-decoder model with attention mechanism. Mayan is a self-contained real machine translation toolkit focused on efficiency and research. There are several model types supported by Mayan frameworks, among them transformer, multi-transformer, share multi-transformer, S2S, multi-S2S, and share multi-S2S models are chosen for doing the experiments. In the experiments, two baseline models are used for English to Myanmar and Myanmar to English translation. For English to Myanmar translation, the baseline model takes English tree data and produce the outputs of Myanmar string data. The multi-source and share multi-source model takes two inputs of English string data and English tree data and produce the outputs of Myanmar string data. For Myanmar to English translation, the baseline model takes Myanmar POS data and produce the outputs of English string data. The multi-source and share multi-source model, two inputs of Myanmar POS data and Myanmar string data and produce the outputs of English string data. Myanmar data in UCSI corpus are not segmentation data, and thus we need to segment these data. We use in-house malware segmenter for Myanmar segmentation and server rate segmenter for server segmentation. To read the proposed model, we need to apply pure tagging on Myanmar data site and 3 data formats on English data site. For Myanmar POS data, the second data were tested by using ARIA model built in MyPOS version 2.0. This is the example of POS test data for the sentence. This means I am a researcher. ARIA model provides the accuracy of 77% of precision, 81% of record, and 79% of error measure. For basic English data, Zen Basa setters, BCLG Basas from Stanford Basa, Belief Basa, Clean Basa, and regular expression Basa from NNTK packet were tested with English data. BCLG Basa and Belief Basa cannot pass the long sentences. Clean Basa and regular expression Basa can pass the long sentence. However, the running time of New Basa takes a lot more than regular expression Basa. Regular expression Basas can pass the long sentences and all experiment data within a few minutes. And thus, we choose this Basa for 3 data formats. This is the sample format of English Basa string produced by the regular expression Basa. All the energy models are trained on 2 GPU with Mayan frameworks. Transformers and S2L architectures are applied in our experiments. Transformer models, multi-transformer models, and shared multi-transformer models are used for the PAS architecture. For the scan architecture, we use S2S model, multi-S2L models, and shared multi-S2S model. The proposed models are evaluated on ANT tests. This table shows the evaluation results of PAS and scan architecture. The first battle the table consider English to Myanmar translation score, and the scan battle the table consider Myanmar to English translation score. For the PAS architecture, in the PAS battle the table, shared multi-transformer model achieves higher blue score than the baseline model. And moreover, multi-transformer models outperforms the baseline model in terms of A and F score. However, the Y score of multi-transformers and shared multi-transformers are lower than the baseline transformer model. In the scan architectures, the multi-S2S models outperform the baseline S2S model in terms of blues and A and F score. The shared multi-S2S model provides better Y score. In Myanmar to English translation, the 2 baseline transformers and S2M models outperform the other models in terms of blues, whites, and A and F score. No improvements occur in this translation test. Translation outputs are analyzed by using WAT database. Slide programs for NIST Story Toolkits SCTK version 2.4.10 is used for doing the data analysis. The VR formulas can be described as the following equation. S is the number of substitution, D is the number of deletion, I is the number of insertion, C is the number of correct words, and N is the number of words in the reference. This table shows the ER score for English to Myanmar and Myanmar to English translation models. Lower the ER score indicate better translation model. For the PAS architectures or English to Myanmar translation, the baseline transformer model gives lower WER score. However, in the second architectures, the shared multi-S2M model provides lower WER score than the baseline S2S model. In Myanmar to English translation, the 2 baseline transformers and S2S models provide lower WER score than the multi-source and shared multi-source model. Due to higher WER score in Myanmar to English translation, the multi-source and shared multi-source models could not provide better translation results. Most of the confusion phase in translation are correct the nature of Myanmar language, the incorrect word segmentation or data cleaning errors or English language. Myanmar language with no article and the different natures and languages of Myanmar language and English language. This table shows top 10 confusion phase of transformer models. The first column a hypothesis phase for English to Myanmar translation, and the task column is for Myanmar to English translation. Although the confusion phase in these columns are called by the natures of Myanmar language. In the task column, the confusion phase of APUS to GOT, GOT to APUS, comma to these, and these to ampersand AMVs are called by the incorrect segmentation or data cleaning areas of English language. In addition, the confusion pairs of D to A and A to D are called by Myanmar language with no article. And the confusion pairs of into all, to off, and with to n are called by different natures and languages of Myanmar language and English language. This may call Myanmar to English translation model has to learn and training process. In conclusion, for English to Myanmar translation, multi-source and share multi-source models outperform the baseline model. However, in Myanmar to English translation, the proposed models could not provide better translation resource than the baseline model. Top 10 confusion phase could be clearly found in error analysis. If these errors can be cleared, the translation performance of the share test will improve. In the future, we intend to apply additive techniques in Myanmar to English translation to improve the translation quality. And also, we intend to extend String to Tree and String to BOS translation approaches for NRE source languages such as Thai and Myanmar. These are my reference. Thank you for listening.
Thank you, Jaja. So I think like this task would be the difficult one, due to the data scarcity, but great work. All right, we have the 3 remaining speakers in this session, and so the next speaker will be the Ye Ko-tu. So the title is the Hybrid Statistical Machine Translation for English Myanmar. UTYCC Team 1 submission to WAT 2021.
Hello, can you hear me?
Yes, we can hear you. And we
Okay.
also see your screen.
Okay. Good morning, everyone. Today I will make a presentation of UTYCC team participation. The title will be the Hybrid Statistical Machine Translation for English to Myanmar. So the team ID is YCCMT1. And I will make the presentation, and these are our co-authors. So this is the first time to participate the WAT 2021 from UTYCC University of Technology Yaranapong Cyber City, Myanmar. So these are the contents of my presentation. So according to the current research trend, we already know most of the researchers are focused on neural machine translation. And however, for the under-resourced languages, for this time, we selected the SMT approach. These are the reasons. So in practically, according to our experience, NMT training, we have to use the GPU hardware, and most of the university in Myanmar, we have a very limited hardware resources. So this is also one important reason. So we want to try with SMT for this competition. And as you all know, SMT engine can be trained on a few 100,000 of parallel data, like the Myanmar English share data. And of course, we can hack the SMT engine. It's mean a kind of transparent compared with the neural machine translation. We can do a lot of engineering things. So we tackle with transliteration for this step. So like other teams, we use the provided corpus. However, we need to make some cleaning. Although we do very limited cleaning. So for example, for the WAT segmentation, we use our own silver breaking because the UCSY training data. Actually, there are two parts of training data. One is supported by the UCSY, and the another one is supported by the NICT ALE data. So for the UCSY data, there's no segmentation at all. So we have to deal with segmentation. So for this proposal, we use our own Silbrick segmenter that we already released. Actually, a regular expression-based silver segmenter that work well for Myanmar language. So these are the number of sentence, number of silver, and for both Myanmar side and English side. So when we see the training data, both of the training data, and we found there are several things that we can work to increase the machine translation performance. For example, there are a lot of translation mistakes, spelling mistakes, and also generally the sentences are very long. So of course, there are also a lot of transliteration word containing. So these three parallel sentences are the example from the corpus. So here, as you can see, in one sentence, it contains two transliteration words, Sydney and Randwick, and like Queensland, and also some shortcuts. For this second example, there are three sentences containing. And here also you can see like California, Britney Spears, Mission, and so on. So especially for the development data, EAT corpus, of course, I also contributed for this corpus building when I was at NICT, so I know about this corpus very well. So I found I know a lot of concentration word are contained in the data, and when we ran a very fast time running SMT and also both NMT, I found there are a lot of a kind of mistake found based on the transliteration word. So what we can do is in a practical way. So we have some members. So I suggest my members, okay, a kind of engineering work. So let we extract the translator word manually, a kind of building dictionary. Then we try to tackle with that dictionary. So we extract it manually from the ARD corpus, of course, except the test data. So these are the some example of extracted word, translation word from the corpus. So there are a lot of variety of transliteration word, translated word, like country name, a person name, like month name like January, March, and of course general nouns like penalty theory, and some organization name like Liberal Democrat, Scottish Premier League, and also contain a lot of abbreviation unit. These Myanmar words are actually all are the out of dictionary or out of the general domain. All are actually translated word. So including some like direct translation. So it's mean not translated word. It's we use the English word directly. That is also not strange actually, because in the daily Myanmar language, many English words we are using in written and also conversation. So these are some examples. So we use the SMD system provided by the Moses, like kind of standard SMD framework. So we use not only the PPSMD, free-space machine translation, we also use other tools like OSM, Operation Sequence Model, and HBB-SMD, hierarchical free-space machine translation. So that three model provided by the model, we use it. And I know very well about the SMD of Moses because I worked many years. So that too provides several a lot of facility actually. So one of the facilities that provide is they provided kind of dictionary insertion to build a hybrid translation. So for our proposal, actually hybrid translation. So as you all know, that there are a lot of approach for hybrid translation. Generally, is integrating the dictionary or some more information to the core MD engine. So we use that one of the XML tag import facility of the SMD toolkit. They provided actually 5 options like exclusive, inclusive, constraint, ignore, and pass through. So I don't want to go in detail. So please refer the manual of the Moses. We can also provide probability value for each word by manually or by some rules. So in this case, we are not playing with the probability value. We just fix a kind of giving us a strong probability value for the extracted dictionary word, and then we put it to the SMD decoder. So although we tested with a lot of all options, but for the paper, we use only 2 options working well for English to Myanmar hybrid translation. So that is only inclusive and exclusive. Others are not very much different. So in practically, we have to prepare the import data in this own way. For example,
Yeah.
this
Sorry
is for
my interruption, but we are a bit running out of time. So can you quickly a little bit faster so that like the remaining speakers like can take enough of the time for their presentation?
Sure. So
Thank you.
these are the format. So these are the comment. So just inserting the XML tag. So these are the results. So as you can see, the results are very clear. The baseline with the normal BBSMT is 15, and we got around 6 blue score. And generally, all are the XML inclusive results. So you can see very clearly. However, for the XML exclusive of hero, there are a little bit problem because as you all know, hero also using the XML tree structure. So we have to tackle with a little bit, but we can manage well, and it's increased. But we need to learn more. So as a discussion here, as I pointed out, there are a lot of still transliteration errors, and some are not consistent. And here you can see same in English word, but different in transliteration containing. So it's actually intonation, and some are totally different. And here also. So as a conclusion, this is very easy to implement. And according to our research and official research, what we try to find out all English to Myanmar translation here right now, and our proposal working well, and is the second top score. However, as I mentioned in my slide, the UCSY corpus is updated annually, so it's not directly comparable. But however, in relatively, we got a very good score, especially to English to Myanmar translation and SysBlue score. So we also provide all experimental results and including member information, everything on our GitHub website. And extra the translation dictionary also we shared for further studies. So here not only our team, actually NECTEC team results also included. So thank you for your listening. These are some acknowledgement, and in the near future we also plan to share some our parallel data to contribute to the WAT 2000 maybe next year from the NECTEC side also. Thank you very much.
Thank you. Yeah, those data will be quite helpful in the MT areas. All right. Okay, so shall we move on to the next speaker? So the next speaker will be Kenji Mamura. So the title is the NICT 2 translation system at WAT 2021, applying the pre-trained multilingual encoder-decoder model to low resource language pairs.
Okay, just a moment. Okay, let's start my presentation.
Yeah, you can start it anytime. We've already seen
Okay.
yours.
Sorry, we cannot hear.
Oh. Just a moment.
今村さん、聞こえません。
はいはい。了解です。Okay. Okay. There are two domains in this task. The ALT domain consists of sentences of which use. The size of the data for training is about 18,000 sentences. The IT domain is translation of software documents. Training sentences were obtained from GNOME, KDE, and Ubuntu subcorpora in the Opus corpus. The training data sizes are 73 to 504 sentences, depending on the language. You probably already know the MBAT model, but I briefly explain it here. The MBAT model is an encoder-decoder transformer. The publicly available model was trained on 25 languages, but does not support Indonesian, Malay, and Thai. To use MBAT model, there are two phases for training. pre-training and fine-tuning. The first phase is pre-training. This process uses multiple modeling corpora and perform a token masking task and sentence permutation task. To train a multilingual model, language ID tags were supplied for the input and output sentences. In the fine-tuning phase, we perform normal training with the language tags using parallel data. As I described before, the original embedded model does not support Indonesian, Malay, and Thai. Therefore, we added the unsupported languages to the embedded model. Specifically, we first added the new language ID tags to the word embeddings with random initialization. In this case, only 3 embeddings were added. Then we additionally pre-trained the model using monolingual corpora extracted from Wikipedia. It took about 15 days. This figure shows the structure of the transformer. There are 3 tensors of word embeddings, here, here, and here. We expanded these tensors to include new language IDs, and then additionally pre-train the entire model. Experiments were carried out using the Fairsex transformer. This graph shows a part of main results. The blue scores of extended pre-trained model, red bars, and the baseline, blue bars. As shown in these graphs, all blue scores of the extended pre-trained model were better than those of the baseline. Almost the same trends can be observed in both supported Hindi and unsupported languages of the original model. The smallest difference was in the English to Malay translation in the IT domain, but an improvement of over 6 points was still achieved. We additionally tested the effect of multilingual training. Even in binary transformer, we can train a single model using byte text of all language pairs. We call it multilingual models. On the other hand, bilingual models were trained using the corpora of each language pair. We compared 2 models. These graphs show the blue scores of the ALT domain. In binary transformer, multilingual training was effective as shown in this graph. However, in the extended pre-trained embedded model, it was not effective. This is because embedded model has learned sufficiently in advance. This slide is not shown in my paper. After submission, I wondered about the effect of additional pre-training. So I evaluated one more setting. That is, if only expand the matrices of word embeddings without additional pre-training, what happens? The results are shown in this graph. The green bars indicate the extended model without pre-training, without additional pre-training. The blue scores greatly improved without additional pre-training for all translation directions. I was disappointed because most improvements came from the original MBAT model. However, scores further improved with the additional pre-training. To summarize, we participated in the next subtask. A feature of our system is we use the pre-trained MBAT model, and we added unsupported languages to it. As a result, the blue scores greatly improved, including the scores for the additional languages. Thank you. Okay.
Yeah, thank you very much. So we have one more talk before the next invited talk. So let me introduce the next speaker. The title of the paper is Raktan's participation in WAT 2021, examining the effectiveness of pre-trained models for multilingual and multimodal machine translation. And the speaker, the first author, is Raymond Hendy Susanto. So please feel free to start presenting.
Hi, I will share my screen. Hi everyone, so my name is Raymond from Rakuten Institute of Technology, Singapore. My presentation today will be on Rakuten's participation in WAT this year, examining the effectiveness of pre-trained models for multilingual and multimodal machine translation. Here is the outline of my presentation today. First, I will give a brief introduction about our participation. Second, I will describe the models in use and their experimental setup. And then I will go through our proposed approaches and show the evaluation results for each of the 4 tasks that we participated this year. Our team is the one with the team ID Sakura, and we participated in 4 tasks this year. We participated in the NICT SAP task in 4 language pairs and 2 domains, IT and Wikinews. We also participated in the multimodal Japanese task, which is the Flickr 30 entities task. Next, we also participated in the multilingual indic task, which involved bidirectional translation between 10 indic languages and English. Lastly, we participated in the ALT Myanmar English translation task. For the models, we use the multilingual pre-trained model based on the MBAT architecture, and this follows a 12-layer transformer architecture. We perform a multilingual fine-tuning on the parallel datasets from NICT SAP, multilingual indic, and also multimodal Japanese task for the unconstrained setting. Second, we train a multimodal model that consists of a 12-layer transformer for encoding the text input and a bottom-up attention model for extracting the image features. We applied this model for the constrained multimodal Japanese task. Lastly, we use a 4-layer transformer for the ALT task, and the train data is smaller in scale for this task. Here's our experimental setup. In terms of data preparation, we didn't use any external resources other than the parallel corpora provided by the shared task organizer. For the transformer models used in the multimodal Japanese task, we tokenize the data using Juman and and Moses for the Japanese and English data respectively. We tokenize Myanmar text using P-Daungsu. After that, we train a sentence piece vocabulary based on the byte pair encoding or BPE. For Embedded fine tuning, we reuse the same 250,000 BPE vocabulary from Embedded, which is originally taken from the XLMR. Note that this pre-processing does not require pre-tokenization. Finally, we also extracted global image features using faster RCNN object detector, which was pre-trained on visual genome dataset. So in the next few slides, I will show the evaluation results for each of the 4 tasks that we participated in. For the NICT SAP task, we perform multilingual fine-tuning on EMBARD 50 on the provided parallel data. We compare our model with the multilingual many-to-many model from last year as our baseline comparison. And in terms of blue score, we observe a significant improvement over this baseline, up to 25 blue points. And this also shows that multilingual models can benefit greatly from pre-trained multilingual language model like EMBARD. In terms of the overall rankings this year, our submission has the highest AM/FM scores, adequacy fluency scores, on 7 directions on ALT and 6 directions for IT. Furthermore, in terms of human evaluation, we also rank first for IT English to Indonesian and English to Malaysian. Moving on, we also participated in the multimodal Japanese task, both in the constrained and unconstrained settings. For the constrained settings, we train a multimodal NMT based on the universal visual representation, which is retrieved from a learned topic image lookup table. An attention layer with gating mechanism is used to fuse the visual representation with the encoded source sentence as the input for the decoder. For the unconstrained setting, we fine-tune the EMBARD 25 model using only the parallel data provided. Our experiments show that both approaches are effective, and using EMBARD alone can actually perform as well or even better than the multimodal model. Under the constraint settings, our submission ranked first in terms of blue and the human adequacy scores for Japanese to English. Next, we will discuss the results for the multilingual indic translation task. So we applied a similar approach for the NICT SAP task. Namely, we fine-tune the EMBARD 50 model on the provided training data. We also extended the original EMBARD model by extending the word embedding layers by random initialization and fine-tune it on the provided parallel data. We also adapted this model on the PMI dataset by further fine-tuning it for 12 and 1 epoch more iterations for English to Indic and Indic to English respectively. We compare against the organizer's bilingual transformer-based model on the 10 Indic languages. And as we can see in the charts that we observe consistent improvement across the language pairs. Our systems ranked second, 6 out of in 6 out of 10 directions for which the human results are available. And lastly, continuing our efforts from last year on the Myanmar to English, Myanmar English translation, we compare different data processing of the Myanmar English training data. In particular, we compare a baseline model without any pre-processing and only using the original training data, and we compare it with various pre-processing schemes to augment the original data with word level as well as syllable level tokenization for Myanmar. And we observe that we can obtain significant improvement by doing so. And we found that this technique might be useful for enriching low resource languages so that we can have more data. So here are the references in our paper, and thank you for listening.
Thank you for your talk. That's a lot of tasks you participated in, so good job. So that's the end of this shared task session. The next is the invited talk. Who is the chair for the talk? Is that Goto-san? Goto-san, can you please take over?
Okay. Can you hear me?
Yes, perfectly.
Okay, so the schedule is behind. So we skip short break and I'll start the invited talk 2 session. So I'm Isagoto and I am the chair of this session. I introduce the invited speaker, Graham Newbick. Graham Newbick is an associate professor at the Language Technology Institute of Carnegie Mellon University. His work focuses on natural language processing, specifically multi-language models that work in many difficult languages, and natural language interfaces that allow humans to communicate with computers in their own language. He publishes regularly in the top venues in natural language processing, machine learning, and speech, and his work has won awards at EMNLP 2016, EACL 2017, and NACL 2019. So the talk title is Understanding and Improving Context Usage in Context-Aware Translation. So please start talk, Graham.
Hello, nice to see everyone. Can you hear me?
Okay, I can hear you and see you.
Okay, great. Let me share my screen. Can you see my screen now?
Yes.
Okay, great.
Yes, I can see the screen.
So I will be giving a talk about understanding and improving context usage in context-aware translation. Thank you very much for inviting me to give the talk. It's nice to be back at WAT after many years. This talk is based on work with Kayo Yin, Patrick Fernandez, Danish Pruthi, Aditi Chowdhury, who are all students at CMU, and also Andre Martins, who's a collaborator at Unbabel and Institute Superior Tecno at in Portugal. Okay, so why is context important for translation? So if we just look at this sentence, we'll have to get rid of that mole. Mole is a polysemous word, so if we have something like things could start to get dangerous if the ministers find out as our context, then this corresponds to a spy. But if we say, could it be anything serious, doctor? This could correspond to a mark on your skin. So if we look at a popular translation service, we can see that it does well enough if we are talking about the spy version of this word. However, with this context, we can see that it makes a mistake and translates it into the spy, despite the fact that this is now referring to a spot on your skin. And this is another example. So in English, we don't have we don't have a gender for it, or the pronoun it or they. However, in French, you need to choose a gender based on the noun that the pronoun is referring to. So this actually is a mistake, and you would need to translate it into the female pronoun here. So I'll talk a little bit about today's agenda, and before I do so, I'll note that all the code and data is available if you want to take a look at it. But today's agenda, what I want to talk about are new methods to measure context usage in MT, including attention agreement with human annotations and conditional cross-mutual information, and also new training methods to increase context usage in MT, namely attention regularization and contextual word dropout. So let's get started. The first items in this bullet point kind of form one coherent thing, and the second two items in the bullet points form one coherent thing. So I'm going to be talking about both, and actually both of these papers were presented here at ACL as well. So for the first one, do context-aware translation models pay the right attention? I'm going to be talking about the agreement with human annotations on what context is important. So if we look at the source input and we look at context-aware NMT output, we can see that, and we look at the attention distributions that the NMT system is generating, what we can see is that when it tries to translate this word L here, or generate this word, it is attending to things that seem like they would not be very important for translating this word. So for example, a question mark here. And notably, it's not attending to the previous sentence at all directly. So what we would like to do is we'd like to first quantify how much NMT models are paying attention to the context when they should be. And also what context is useful during ambiguous translations. And if the models are not paying attention to this context, can we encourage them to do so? So first, I'm going to talk about how we identify what type of context should be useful in translation. And the way we do so is through a human study, where basically what we do is we ask human translators, in this case, English-French translators, to decide between one of two ambiguous outputs. So here it's male or female, masculine or feminine gendered pronoun. And after they decide between these two, they identify the context that was useful to them in making this decision. And when we also do this for word sense disambiguations, so like the mole example that I gave before, and they can identify which type of context was useful to them. And finally, we also have different amounts of context that are available to them at any time. So some of the time we give them lots of sentences of context, sometimes we give them no sentences of context. And the reason why we would like to do this is we'd like to identify cases where context is genuinely necessary to perform the translations. So then the question becomes, what context do translators use? And what we do is we show them these variety of tests, and we have them annotate the contexts. And we do this for both pronoun anaphora resolution and word sense disambiguation, like I said before. So if we look at the pronoun anaphora resolution case, we are basically asking them to identify which of the two masculine or feminine pronouns should be used. And we have them identify the context that was useful for them. One interesting thing about this task is actually you might have to go back several sentences before you identify exactly which word it was as well. So you can have these chains of pronouns too. So one interesting thing to note here is that on the French side, you can look back maybe one sentence to find that the pronoun was a masculine pronoun il. But if you look on the English side, you'd actually have to go back multiple sentences to see if what the identity of the pronoun was before you could decide whether it should be a masculine or feminine pronoun. So you can see that these things get kind of tricky. And kind of because of this, a priori, we would expect that, maybe target side context would be more useful than source side context in this case. So we also tried with word sense disambiguation. And one thing that we found was that actually word sense disambiguation largely relies on the current sentence. But one thing that's very important for it, or that we would hypothesize would be important for it, is, for example, what the subject is or what the object is. And so because of this, we would need to basically have a balanced set of context on both the source and the target side, because it's not the case that we have this kind of asymmetric distribution of gender like we have in the pronoun case. So what we did essentially was we did this human study and we created this for 14K sentences, and we named this supporting context for ambiguous translations dataset, the SCAT dataset. And we have released this for other people to use if you're interested in using it to either train your models or test whether they're good for translating these sort of phenomena or identifying the context that's necessary for these sort of phenomena. So the next thing that we wanted to take a look at was whether models are paying attention to this context or not when they actually do translation. And so for a model, of course, we have our standard encoder-decoder model. It could be a transformer model, for example. And what we do is we basically append up to 5 previous source sentences and 5 previous target sentences when we are calculating the current target sentence. So basically, this is not a really complicated model. It's just a standard NMT model with additional context added on. And we train the model on the open subtitles dataset, which is a dataset of subtitles, of course, that also have context. So then in order to answer our question, what we would like to do is we would like to quantify the alignment between human annotations and how the model is attending to particular words in the source or target side. So the way we do this is essentially we get the attention distribution and we can treat the attention to the human context as kind of a one-hot vector, and the attention distribution as a kind of normalized probability style vector, and measure the overlap between them. And we have a number of different ways to measure the overlap in the paper. But the particular one that we did here was that we're showing here is basically what we do is we sort the order of the attention distribution, and we see how many basically steps it takes before we find a context that is annotated as true. And this is called the quote unquote probes needed evaluation metrics. So the fewer probes needed, basically the better alignment we have with the human annotations. So if we look at the probes needed and we look at the uniform distribution, we can see that we would need about 13 probes before we got the human annotation. And then if we look at the self-attention, the decoder cross-attention, and the decoder self-attention, we see that the encoder self-attention actually has significantly fewer probes needed than the others. So we can tell that in this case, the encoder is doing a little bit better at identifying the context needed. But actually, the decoder self-attention is doing surprisingly poorly. And this, I guess, is a little bit of a surprise, perhaps, because we would kind of expect a priori that the target side context would be more useful. But we can see that basically context-aware translation models aren't doing an incredibly good job at identifying the context that is needed to perform translation well. So based on this, what we'd like to do now is we'd like to take the scat annotations and get them to train our model to do a better job of translating. And so the way we do this is using a fairly standard technique for attention regularization. And basically what we do is, in addition to the log likelihood objective, we add another objective, which is equivalent to the KL divergence between the normalized human attention alignments and the model attention. And what this does is basically this tries to encourage the attention to look more like that for the scat annotations. And this is only done for the data where we have such annotations. So namely only for pronouns, for example. So then what we would like to know is, if we do this sort of attention regularization, does that actually improve the accuracy of the system? And we measured this through two evaluation metrics, Blue and Comet. Blue is the one that we're all aware of, and Comet is basically a better evaluation metric that more closely correlates with human evaluation using embeddings and ranking and other things like this. But basically, Comet is like Blue, but better. And then we have a pronoun F measure. And what this is we look at how often the translation system generates the correct pronoun. So this is a more focused evaluation telling us whether the model is able to generate the appropriate pronouns in translation. And also something called contrastive evaluation, where we ask the model to score a correct sentence and an incorrect sentence, and see what percentage of the time the model picks the correct sentence instead of the incorrect one. So if we look at the various scores, we have the baseline here. And what we can see is that adding attention regularization improves all of the scores. It improves Blue a little bit, 0.4, Comet about 0.6. But more notably, it improves pronoun translation accuracy and contrastive evaluation by multiple percentage points, 6 percentage points or 9 percentage points. And so basically this shows that if we do a targeted evaluation focused specifically on these phenomena, we get better results. Another thing that we can see is this attention regularization also improves the quality of the attention distribution. So the probes needed measure that I talked about before basically is decreased pretty significantly, which demonstrates that the model is paying attention to kind of the correct context that was annotated by humans. And now we can see with the attention regularization that when it translates the pronoun, it attends to the actual context that would be useful to translate this pronoun. So we have a whole lot of other things in the paper, and I'd encourage you to take a look if you're interested. But basically, we demonstrate that there's increased usage of supporting context. We also check that regularizing encoder self-attention contributes the most to the improvements. However, one interesting thing we found is that there was little difference in word sense disambiguation performance. And the reason for this was precisely because word sense disambiguation, even for humans, did not seem to benefit as much from extended context. So that's the first part of the presentation. And now I'd like to move on to the second part of the presentation, which is also about measuring and increasing context usage in context-aware translation. But instead of using human annotations, this is kind of a general purpose method that can increase, can measure and increase context usage without respect to annotation or, even considering specific phenomena. So many approaches have been proposed for context-aware MT. Concatenation, like we used before, multi-encoder cache-based methods, hierarchical attention. But most of these approaches fail to outperform baselines with respect to the blue score or comet or other things like this. And this is particularly the case in high resource scenarios. And the question can become why? And one thing we hypothesize is that models underutilize context even when able to use it. And quantifying context usage in general is tricky. In the previous presentation, I talked about quantifying context usage for specific phenomena using human annotations, but obviously we can't annotate absolutely every piece of context that is useful. And so what we'd like to know is, can we do better than what we do now? So for measuring context usage, we chose to take, in this paper, we chose to take a mathematical approach. And basically, recently there has been a paper by Bugliarello et al. That proposed a method called cross-mutual information. And basically what this tried to do is this tried to say, how much information do we gain about a sentence by knowing its translation? And so this is kind of interesting because what it does is it tells us how much more likely is a sentence when we know its translation than if we just calculate with respect to a language model. So this is interesting, but this is not telling us what we want to know for this, for the purpose of this work, which is how much does context help us in a translation setting. So what we do is we propose conditional cross-mutual information. And what this means is we take a standard MT system, like a sentence-based MT system, and we measure how much we gain by adding additional context. So what this is telling us is how much more likely does the sentence that we are trying to generate get when we add context. So one notable thing here is that we have an MT system that's sentence by sentence and an MT system that is contextual. And so this is kind of an illustration here. So when we have the uncertainty over translations given the source and context, this is our CXMI here, basically, how much does our uncertainty decrease? One kind of important point here is what considerations do we need about these two MT systems? And an important thing is that we want to make sure that the differences between both probabilities are due to context and not other factors. So basically what we do is we train a single system that is able to handle both context and non-contextual settings. And the reason why this is important is because, as we all know, training a neural MT system is very dependent on a whole bunch of different things, the random initialization, the data ordering, other things like this. So by training a single system, that's able to both handle context and not context, we can basically account for this issue. So now I can jump into the experiments, and in the experiments, we considered document level translation task, IWSLT 2017 for both English German and English French. And we also consider a pre-trained setting with a large model where we pre-train a sentence level model on Paraqual to make it a very strong model and then fine tune it with context. We also evaluate on contrastive data sets for pronoun resolution and lexical cohesion like we did in the previous presentation. So how do we get a single model that's able to translate with or without context? And the answer here is simple. Basically, we train a model by sampling different context sizes when we translate. So it may be given either 3 sentences of context, 2 or 1 or none. And so that gives us a model that can translate with different context sizes. And we can then use this model to measure CXMI for different levels of context. And we can do this on both the source and target side. So here are the results of our CXMI metric with different sizes of context on the source and target side. And what we can see is that in all cases, if we add more context for the first few sentences, or for the non-pre-trained model, if we add more context for the first few sentences, the CXMI goes up, which is kind of indicating that our model is doing better with more context. As we add more target context, it still maybe goes up a little bit or levels out near the end. The source one actually goes down, indicating that the model is not able to better use large amounts of source context. For the pre-trained model, interestingly, the source context is somewhat useful, but the target context is very useful. And the reason why this is interesting, particularly interesting, is because this indicates if we kind of know information about the target style or something like that, that is particularly helpful. But on the other hand, if we just know about the source, we get kind of a minimal amount of information. We also measured CXMI and correlated with other kind of measures of context usage, such as pronoun-based contrastive evaluation or lexical cohesion-based contrastive evaluation. And we can see that CXMI tends to correlate with how well models do on these other metrics. So another question we may have, like we had before, is can we use these intuitions from CXMI to increase context usage? And unlike before, we now don't have any supervision. So we would like to take a less focused, but more general method for doing so. So the way we propose to do this is essentially by a method that we called contextual word dropout or co-word dropout. And the basic idea is that we calculate a mask over sentences, but we only calculate the mask over the current sentence. And the reason why we only calculate the mask over the current sentence is because we would like to encourage the model to use over the source side of the current sentence. And the reason why we do this is we would like to encourage the model to use other context other than the actual sentence it's translating right now. So if we have a previous context sentence, we might mask out some words in the current sentence, but we won't mask out words in the contextual sentences. So we did experiments with this method, and we saw a couple things. The first thing that we found was first that by adding more of this co-word dropout, this consistently increases the context usage on the target side. So basically, the CXMI increases a little bit when we have this dropout set to 0, but it increases much, much more as we add more of this dropout. And then we also assessed it on translation quality, training 4 models with increasing levels of co-word dropout, a baseline model with no context, a 1-to-2 model with 1 target sentence, and a 2-to-2 model with 1 source and 1 target sentence as context, and a multi-encoder 1-to-2 model. So this is kind of a different model architecture that encodes context and non-context sentences differently. And reevaluate on blue and comment again. Basically, what we can see is that co-word dropout seems to improve performance in all cases for non-pre-trained models. Interestingly, the blue score goes up by a little bit, 0.9, but the comment score goes up by quite a large margin, indicating comment sensitivity to important words influenced by context. And in the pre-trained setting, co-word dropout also helps a bit. The gains are much less large, but it still helps with respect to comment, particularly in the 2-to-2 setting. It also helps with the multi-encoder architecture. So we found that the multi-encoder architecture improves quite a bit more, actually, maybe indicating that this architecture has a little bit more inductive bias or capacity to learn when encouraged to do so properly. So the improvements are noticeable when evaluating on contrastive data sets as well. So we can see, a 5-point increase in contrastive evaluation with respect to pronouns. And for the pre-trained model, the gains are smaller, but still visible to some extent. And one interesting thing is that for the multi-encoder model, actually co-word dropout allows the multi-encoder model to beat the baseline, where it would not have beaten the baseline if it was not included. So that's all I have for today. Basically, my summary is that we have proposed new methods to measure context usage in MT and a few new training methods to increase context usage. I'd encourage you to check out the papers for many more details and the code and data if you'd like to use them. And for some future directions, we're thinking about, can we quantify on a more fine-grained level under which circumstances we require context? And this is actually some ongoing work we're doing multilingually as well in creating a corpus to do this. So I'd be happy to follow up with anybody who thinks it's interesting. Also better understanding of context usage across languages and phenomena. So, here we did English, French, and English, German, but, things would be very interesting in Japanese English, for example, because there's lots of contextualization that goes on in Japanese. And also better methods to increase or optimize context usage. So we proposed 2 very simple ones here, but there's all kinds of other methods that we could think of. And we hope that, for example, the SCAT dataset would be a good way to kind of measure the effect of these methods, for example. So yeah, that is all I have for today. Thank you very much. And I'm happy to take questions if there's time to do so.
Thank you for the interesting talk. So are there any questions or comments?
I have one question. Is that okay?
Okay.
Okay, so it's related to the future direction, right? How can we quantify under which circumstances we require context? And the question is, how do we even guarantee that unnecessary context is not used? Because have you seen any cases where you specified the context, but that actually reduced the performance instead of improving it? So do you have any comments on that?
Yeah, and actually we have a very clear example of this in the second thing here, where adding more source context actually, hurt the model. I think, or hurt the CXMI. I think that's a very good point. And I think attention regularization is maybe one way to help supervise the model and get it to not pay attention to context. Another way that I've thought about, but we haven't actually experimented with, is maybe adding completely irrelevant context and getting the model to try to avoid using that. So, you sample in a random context and you try to get the model to not pay attention and not give any attention weights to the random context. So I think there are certainly ways to do this, but it's a good direction for future work, I think.
That's interesting. So if we take some random context and do some kind of a contrastive training per se, like tell the model that, okay, in this situation, definitely do not rely on the context.
Yeah, that would be one example.
Okay, awesome. Okay, so my one small technical question is, when you use context on the decoder side, while decoding, do you use the gold standard sentence or the previous translation that was generated?
Oh, so that's a very good question. I don't want to be to say the wrong thing here because we tried both, and I believe the results there are results in the paper for both, but the results shown here are using the gold standard context.
Okay. The reason why I asked is because with the gold standard sentence, it kind of makes sense that the context on the decoder side would be much more relevant. But I wonder if the decoder makes mistakes while generation, whether this relevance would still hold in that situation.
And that's absolutely correct. When you don't have the gold standard, the usefulness of the target decreases, but it still is useful.
Okay, and this information is in the paper, right?
Yes, I believe.
Awesome.
So.
I'm going to go through that. Thank you so much.
Great, thanks. I see one question in the chat. Hi, Sudo Sensei. How can we evaluate the translation results considering context? So that's a very good question. There's actually, been a fair amount of work on evaluation over the past, 1 or 2 years on human evaluation that shows that you need to show human evaluators context in order for them to evaluate accurately. And that even can affect whether, a model is determined to be as good as a human translator or much worse. So I think for human evaluation, definitely we should be showing results in context instead of like individual sentences, for example. Also recently, there's been a lot of interesting work on trainable evaluation metrics that basically learn using embeddings. So something like Comet, for example. However, as far as I know, I might be wrong on this, but as far as I know, I think most of those trainable evaluation metrics don't look at context. They're only sentence by sentence. So that's an obvious, interesting, future direction. How much could we get trainable evaluation metrics to improve by giving them context? And do we need to use any of the tricks that we presented in this paper, in these papers, for example, in order for them to use that context effectively, I guess? So yeah, I think that's a really interesting question, but I don't necessarily know the answer.
Thank you for the answer. I have a comment on the answer. So the use of context in machine translation evaluation is also
equally difficult to use the context in translation itself. It's really difficult problem, but also very interesting. Yeah. Thank you very much.
So, are there any comments or questions?
So I have one more question, if it's okay.
Okay.
So in the case of pre-trained models, like in other words, in an extremely resource-rich situation, the target context, of course, seems to be useful, but the source context is not particularly useful. So, like, is there a way to interpret this in more simpler terms? Is it the case that we should not be relying on source context at all, or like what's the best way to summarize that particular sentence, that particular outcome?
So I don't think the source context is not useful. I think the source context could be, so one thing, maybe I misspoke somewhere, but I think that it's not necessarily measuring whether the source context is useful, but rather whether the current model is able to make good use of it. So, so I think source context certainly could be useful, but maybe this model was trained without co-word dropout. So maybe maybe if it was trained with co-word dropout, it would be better. I'm sorry, I don't have it on the slides here, but I'm pretty sure it's in the paper.
Just as an estimate, what was the blue score for this pre-trained model? Like, was it in the upper 30s or something? Okay. So it's pretty high.
Yeah.
Okay, awesome. Okay, thank you.
So did we see improvements in translation related to contextual phenomena with co-word dropout? Yeah, that would be the contrastive data sets, and there are improvements, particularly with respect to the 2-to-2 one, but the improvements are a little bit less obvious for the pre-trained model here. So basically the answer is yes. Human evaluation would be very difficult for context-dependent translation. Yeah, I agree to some extent, but there is papers, for example, by Samuel Laubley and Rico Senrick and others that demonstrate that indeed the results are different for translation in context. So I think it definitely is better to consider context when doing human evaluation. Yeah, thank you very much, everyone, for all the questions.
So are there any questions or comments?
Hello, this is Jay, Professor Newbeck.
Hello.
Yeah, I have one confirmation. So if I'm not wrong, if I understand well your presentation, so let me say, if I want to work for a new language, I might need to prepare context labeling or data. Is it right?
So when you say context labeled data, do you mean translations with context sentences? And if so, then the answer is yes.
Yes.
But you don't necessarily need to create attention annotations. The attention annotations you only need for the first method that we proposed, and the second method, co-word dropout, can be done without attention annotations.
Yeah, I see. So for the second paper, yeah, we can apply. Okay, thank you very much.
Thank you.
Okay, so time is a little behind. So thank you for Bram. Nice invited talk. And let's move on to the next session. So we will take a short break or no? Next chair is Mino-san.
Yes, maybe there is behind the schedule, so I want to start the next session as soon as possible, right?
Okay, so please start.
Yes. So, hello everyone. I'm Mino from NHK, and I'm the chair of this session. In this session, there are 4 papers, 4 presentations as research paper and finding 1. And so let's move the first presentation. The first presentation is BTS, back transcription for speech to text post processor using text to speech to text. Park, could you start the presentation?
Yeah, okay.
Oh, thank you. So start.
Okay, I'll represent. Hello, my name is Chanjun Park, and my affiliation is Korea University. I present a paper called BTS, Back Transcription for Speech to Text Post Processor using text to speech to text. The order of the content is as follows. I will present the introduction. Automatic speech recognition is a technology that converts human voice into text. Performance of ASR has been improved considerably with deep neural network, and lots of companies are trying to apply this system to their business. ASR using pre-trained model with transfer learning shows superior performance compared to the conventional ASR architecture. However, there are 2 main limitations to integrate it to the real-world services. The first problem is the data aspect. ASR using pre-trained model is strongly dependent on the size of the data and difficult to apply to a low-resource languages. However, recent studies not deeply consider on difficulty of getting sufficient performance when low-resource language without any special processing. Second limitation is the service environment aspect. It requires high resource setting with sufficient computing power, such as multiple GPUs, to process large-scale data. However, it is difficult to establish a suitable hardware to provide practical service service except for global companies. Therefore, we thought that there is a need of method which can also provide excellent service to both low and high resource languages, even in low resource setting. To achieve practical scenario, we more focus on designing a new approach for improving ASR performance instead of pre-trained model-based transfer learning. We attempt to improve the performance of the ASR model through a post-processor and data generation method without changing the model architecture. This approach does not require a large amount of data for pre-training the model, and it can be applied to any model, as well as the models that can provide sufficient service with CPU, such as a vanilla transformer. In this regard, this method can elevate the above-mentioned limitation in terms of the data and service environment. Hence, this method is particularly important from the viewpoint of low-resource languages. Accordingly, we propose a back transcription, a fully automated data construction method for sequence-to-sequence based post-processor model that does not require human intervention or model modification. Following the introduction, I will present a related work. ASR post-processing is a research field that aims to improve performance by correcting the ASR errors rather than changing the model architecture. There are 2 main methodologies for ASR post-processing in the field of speech recognition: conventional methodology and sequence-to-sequence methodology. The conventional methodology is based on the rules and statistics. Companies attempt to apply linguistic rules or build their own rules to improve the quality of the speech recognition results. The drawback of this methodology is that it involves high costs and requires a long time to produce abundant rules. Moreover, conflicts between rules may occur and each component must be implemented independently. So some post-processing studies have been conducted using the N-gram language model. The sequence-to-sequence methodology corrects the error in the same way as the machine translation process. Based on the sequence-to-sequence model, the result of the speech-to-text is refactorized using an encoder and is then decoded to generate the human-modified sentences. This methodology outperforms the conventional method based on the rules and statistics. However, the ASR post-processor based on sequence-to-sequence methodology still has some limitation in terms of the data construction and industrial service. First of all, if we take a closer look at the related work of the data construction, there are no open data available for training, and a parallel corpus must be manually built for the ASR post-processor. Manually constructed data, such as speech recognition sentence and human post-edited sentence, need to involve human intervention to transcribe the speech with considerable time and costs are required. Additionally, quality differences may occur depending on the transcriber, resulting in performance degradation of the model. Secondly, although most recent NLP studies are based on the pre-trained fine-tuning approach, small and medium-sized enterprises lack sufficient hardware. Hence, there are many limitations in terms of using technology to service NLP application software owing to low speed and insufficient memory. Hence, we aim to elevate this limitation of the sequence-to-sequence-based data construction through BTF using text-to-speech-to-text. This method can reduce the cost, time, and required for the data construction and is free of the quality issues related to the human transcription. Also, in this study, we use a vanilla transformer, which can be easily applied to required service. In contrast to previous studies, we conduct an experiment on the Korean language, which is a low-resource language, and we make the model constructed in this study freely available. Following the related work, I will present the proposed method. In this study, we introduced the 4 mainstream attributes reflecting the readability and the satisfactority of the ASR service in order to provide a high-quality service to end user of our BTS mechanism, which can be used for training the ASR post-processor. The first limitation is related to the segmentation. The spaces are generally not adequately separated in speech recognition results. To solve this problem, many studies have investigated an automatic spacing module. However, few studies have focused on only ASR. Thus, the satisfactority of the ASR service, which is used by end user, the speech recognition result will lack credibility if this problem is not resolved. The second limitation is a foreign word conversion problem. For example, for the sentence, the loaded tower is on the 123rd floor. The ASR survey output, the loaded tower is on the 123th floor. In other words, loaded tower is not converted in the English loaded tower. We refer to this problem as a foreign word conversion problem. Although it is not a critical problem, solving it can improve the readability and satisfactority of the ASR system for end user. The third limitation is related to the punctuation, like period, comma, exclamation, and question marks. For instance, the correct outputs of the ASR system should be where are you going? However, the general ASR system, where are you going without question mark? Thus, the lack of punctuation makes it problematic for end user to understand the purpose of the sentence segmentation. This could lead to complex issues in the recognition of end user utterance intention in terms of who wants to use the output. The first limitation is related to spelling errors, which frequently occur in the ASR result. Although previous studies have investigated spelling correction, few have focused on the only ASR. So we aim to apply the BTS mechanism to mainstream attribute, as I mentioned in background. So we investigate TTS and SAT to create pseudo-parallel corpus for ASR post-processor, and we call this round-trip process as a text-to-speech-to-text TST. This process can be explained in terms of the machine translation. Source sentence is substituted for the output of TST, and the original monocorpus is substituted for the target sentence. The source sentence has ASR errors generated through the both TTS module and SAT module. However, the monocorpus as the target sentence is grounded well in space, can handle foreign word conversion and special symbol tokens, and rarely involves the spelling errors. We utilize the gap caused by the TST to develop a high-quality ASF post-processor based on sequence-to-sequence training. The figure shows the proposed method, including the BTS architecture and ASF post-processor architecture based on sequence-to-sequence training using the pseudo-parallel corpus, which is derived from the BTS. The model of the left shows the target sentence as a grounded sentence converted into the speech using the TTS system, which is then converted into the source sentence as an error sentence through the STT system. The model on the right shows a sequence-to-sequence based ASF post-processor, which uses the speech of the source sentence as the model input and the target sentence as a ground truth. In the BTS module, the pseudo-parallel corpus consists of the target sentence from the monocorpus and the source sentence converted from the TTS output into the STT output. The source sentence includes the above-mentioned errors. Finally, we can train the ASF post-processor using the pseudo-parallel corpus. The advantage of the BTS method in terms of the service can attribute to 5 factors. First of all, BTS can build infinite training data for ASR or other purpose. In general, building a parallel corpus is expensive and time-consuming. Moreover, it is difficult to establish a high-quality parallel corpus. However, we can easily build an infinite parallel corpus if we exploited the advantage of the monocorpus through web crawling. Second, BTS supports a universal method for integrating a solution to problems such as spacing, framework conversion, and punctuation and spelling errors using a single model, as the monocorpus that is used in our method is free of the above-mentioned problem. Previous studies have been conducted independently, whereas our method can resolve these issues simultaneously. Third, commercial ASF systems such as Google Cloud Speech API can be converted into the domain-specific ASR system. If a TTS is produced using only a single corpus of the specific domain, and post-processor is creating using constructed parallel corpus, the commercial ASR system can be serviced with a domain-specific ASR. Companies build their own ASR system rather than using a commercial system because of the need for domain-specific model, which can be built by exploiting the high recognition rate of the commercialized systems through BTS. First, our method does not require or significantly minimize human intervention for building a parallel corpus, as it involves automatic generation. Therefore, it achieves a significant time and cost saving. In addition, it is free of the quality issues that may arise in the case of the different human transcriptors. Finally, language extension is simple and convenient. The commercial system provides various TTS and STT language-specific API services. Therefore, we can collect a diverse language dataset for BTS. In summary, BTS is a practical solution that can enable companies to provide ASR service. Next, I'll explain about the experiment. The parallel corpus for experimenting with BTS. The parallel corpus for experimenting with BTS was set to Korean, which is logicious languages, and we collected from the 2 different sources. First, we extracted a sentence from the business and technology TED provided in a script translated into Korean. Second, we extracted a sentence from the Korean English translation corpus in AI Hub. For TTS, using the monocorpus, we converted the text into voice data in the MP3 format using Google TTS API. For STT, voice data constructed by TTS use neighbor global speech recognition API to proceed with a conversion back to text data. More detailed numerical explanation, please refer to the paper, please. In the case of the pseudo-parallel corpus built through the BTS, some source sentences are empty or too short. They are not recognized owing to the unintentional errors in the STT and TTS system. Thus, we use the parallel corpus filtering methodology to obtain only high-quality data. A total 1,669 sentences are filtered, and most of which are low-quality data obtained because of poor recognition during STT. We compared the performance of the parallel corpus filtering driver model with that of the non-progress model to verify the effectiveness of filtering. For detailed numerical explanation, please refer to the paper. For the post-processor, we trained the vanilla transformer with pseudo-paracouplet generated by the BTS. The hyperparameter setting were same as those used by Baswani. Further, we use a sentence piece for software tokenization and set the vocabulary size to strict to K. We conducted a statistical analysis of the constructed corpus and comparative analysis with and without PCF. The results are summarized in Table 1. First, we conducted Bayesian analysis, such as number of data and number of tokens and average length of sentences. Second, we analyzed the Korean and English tokens. In the case of K tokens, in the training and validation tested were lost in the source sentences. Token loss is a reason for the omission of the sentence endings and suffixes, and it estimated that the model reflects the common characteristic of Korean speakers who pronounce the ending in slurred manner. Third, the most significant loss was in the case of special symbol tokens. For example, periods, commas, exclamation mark, and small brackets, which are added to describe the situation in transcription of the original data, tend to be lost in the source sentences. Such special symbol tokens may sometimes contain extra colloquial tones or emotion that are not represented by the text adequately. Thus, excessive omission of the special symbol token is equivalent to the loss of the rich representation information of colloquial forms that are different from the written ones. First, we verify the spelling correction performance of the BTS by ASL post-processor. We employ the GLUE and BLUE as a performance evaluation matrix. Base refers to the BLUE score between the source and target sentences. We leverage it as a baseline for assessing the performance improvement. In addition, we compare the performance with that of the Korean spelling error correction model proposed by Park, who performed ASL post-processing experiments and published the model as a demo system. Our results show that paracorpus filtering can improve the correction performance. BLUE and GLUE scores of the no-filter model were 55.72 and 46.23 respectively. BLUE score was higher than that of the base model by 13.53. Further, BLUE and GLUE scores of the filter model were 56.56 and 46.94 respectively. Thus, parallel corpus filtering can promote the performance improvement. Furthermore, these results also show that our post-processor can achieve higher performance in spelling correction. Secondly, we verify the performance of the BTS-based post-processor in automatic spacing. To measure the multi-class accuracy, we use the F1 score to correctly locate the spacing in the target sentences. As a filter model achieved a better performance, further experiments were based on the filter model. Using the post-processor, we achieve a score that was higher than that of the base model by 2.26. Thus, BTS can promote the correct automatic spacing. Also, we demonstrated the performance of the BTS-based post-processor in foreign word conversion compared to the base model. Our processor yielded a score that were higher by 7.54 and 19.27 for Korean and English word conversion respectively. Finally, we verified the performance of the BTS-based post-processing in punctuation attachment. The performance score of the BTS-based post-processor was 16.13, higher than that of the base model. For the base model, the F1 score of the punctuation attachment was 0.89, which indicates the base model rarely achieved the correct punctuation attachment. For example, even though the question mark, exclamation mark, and the comma are very important punctuation to know speaker intention, commercial STT system cannot catch these signals. In conclusion, we have shown the performance improvement for the 4 above-mentioned criteria. Furthermore, the overall F1 score calculated by considering all these criteria in one step showed the improvement of the 8.89. In addition to the quantitative analysis described above, we also perform the qualitative analysis. First, the post-processor can correct foreign word conversion errors. Second, it is possible to correct punctuation attachment errors in appropriate spacing, which frequently occur in the ASL model. Third, the BTS-based ASL post-processor can correct the spelling errors or improper sentences ending generated by the speech recognition system. In particular, for Korean, improper sentence endings often lead to different interpretation of the whole sentences. This issue can be effectively rectified by our model. In summary, we propose BTS, a simple and effective method for generating ASL post-processor training corpus without expensive human labor. We discuss the characteristics of the effectiveness of our approach on the basis of extensive quantitative and qualitative evaluation. We present the generated parallel data and post-processing platform to make our result publicly available. Thank you for listening to my presentation. And if you have a question, feel free to contact my email. Thank you.
Thank you, nice talk. So I'll accept one short question. Is there any question from audience? If no, I have one small question.
Yeah.
I want to ask you about the auto vocabulary problem. And in your paper, you said about the importance of auto vocabulary. In your method, this problem can be solved or deal with this problem?
Yeah, of course it can solve. And moreover, in the future study, I will adopt the copy mechanism to elevate the auto vocabulary problem. So maybe copy mechanism can more elevate this problem.
Oh, I see. So it's up for the pre-processing, right?
It's just like a model modification, maybe copy.
Model. Okay, copy mechanism.
Adopting the copy mechanism. Yeah.
I see. Okay. Thank you. So is there any questions? No. So thank you for the presentation, Park.
Yeah, thank you.
Thank you. And I'll move to the next presentation, zero pronoun data augmentation for Japanese to English translation. Could you start the presentation, Lee?
Sure. Can you hear me?
Yes.
Okay.
I can hear you.
Wait a minute.
And I can see the slide.
Okay.
But it's not full screen.
Wait a minute. I want to open like a tool. Okay. Wait a minute. Slideshow. Oh, wait a minute. This is wrong window. Okay. And then okay, now can you see properly?
Yes.
Okay, thank you everyone. So let me start my presentation. I'm Ryokan Lee from the University of Tokyo. I'm here today to talk about our research, zero pronoun data augmentation in Japanese to English translation. Okay, so in this research, we focus on translation from Japanese to English. Let me illustrate the problem using this example, like translation from unagi ga tabetai na to I want to eat eel. Speaking of eel, in Japanese tradition, there is unagi or eel day during the summer season. Japanese people are encouraged to eat eel on that day, on that specific day during summer. I think it was last week this year. Yeah, by the way, I didn't eat eel on that day, but this is a long tradition from the Edo period. Okay. By the way, like it recently has been said that eels are on the verge of extinction, so maybe we will eat less and less eel in the future, or eat something like artificial eel developed by biotech or something. So today's talk is not about eel, but about translation, but about like artificial data. Let's get back on track. One of the problems in Japanese to English translation is zero pronouns. If you know Japanese, you might notice that in this example, there's no word like meaning I at the Japanese side. Japanese is a pro-drop language where you can drop pronouns when they can be inferred by the listener from the context. Those drop pronouns are called zero pronouns. So in this research, we tackle the problem of zero pronoun translation. Before describing our approach, let's think about how we human infer zero pronouns. For example, hearing an utterance like this with a zero pronoun, the listener might consider this kind of information, like who is talking, or what's the topic of this conversation, or what entities are already introduced in the discourse. Because zero pronouns typically refer to someone or something already introduced in the conversation, or something we already know. We call this kind of information global context. Here, global means the information is outside the sentence. Generally speaking, modeling this global context is difficult. And as far as I know, there is little research on incorporating these kind of global context information into an MT system. So what else we can do? Sometimes we can infer zero pronouns from local context. In this example, the Japanese phrase like unagi ga tabetai na and the word or phrase like tai na indicates the desire of the speaker himself. From this information, the listener can infer that the dropped pronoun is the first person singular, so the subject is the speaker. In this research, we focus on this kind of local context, ignoring global context. So this kind of a bit of summary of this research. In this research, we propose a method to improve zero pronoun translation by facilitating a model learning to use local context. Okay, then next, I'll describe what we did. Our proposed method aims to, okay, so there the correlation between local context and the zero pronoun. And the correlation already exists in the training parallel data. Like if there is a parallel data, like unagi ga tabetai na and I want to eat eel, the model can learn maybe this phrase tai na will indicate the first person singular as a subject. So in theory, with a sufficient amount of data, NMT models can learn how to translate zero pronouns from data. But it is often the case that we can't prepare a large amount of data, especially in the conversational domain where zero pronouns are prevalent. So we turn to data augmentation to create artificial data. What we want is training data with which NMT model can learn how to translate zero pronouns with a clue of local context. So here's a standard pipeline of training NMT system, train corpus and get data and feed it into a system. So in our proposed method, we create artificial training data by deleting pronouns in parallel data, like this. In this example, the word anata ni is kind of like object, and anata is you. So we delete that phrase, but it's still grammatical and understandable. So we create this new data and use that during training. So this is what we did. Very a simple method. I'll elaborate a bit more in detail how we do this. So we first create a list of pronouns and particles. Particles are like case markers in the Japanese language. And specifically, we used a morphological analyzer like MCAP to extract personal pronouns and particle from the training data and make this list. And with that list, we go through the training corpus and find pronouns followed by particle. We have to delete particle together to make it grammatical. And in the list, so delete pronouns in the list. And this is done by simple string matching. Yeah, then we just delete it and then make a synthetic parallel data. That's it. So we train a model with this method and evaluate it. Okay, experiment. So for the experiment, we used Japanese and English conversation corpus, which was created last year by our research group. the number of training sentence is around 240K, and after applying our data augmentation method, it is 240K. For the translation model, we use the transformer model. The configuration is a bit smaller than the famous transformer-based configuration because we thought like the base model is too large for this amount of data. You can find the details on the paper. And we evaluate the translation systems with two metrics, BLUE and zero pronoun evaluation accuracy. BLUE is the famous metric, or now the infamous metric. So I think everyone does not need explanation for this, but for the second metric, like pronoun evaluation accuracy, I need a little bit of explanation. How we evaluate this? We evaluate this zero pronoun translation accuracy with a dedicated data set. There is this kind of data set, which is for Japanese to English translation. This data set contains 724 triplets, which consist of a source sentence. This is a toy example. This is not an actual data. Source sentence and the correct target sentence, reference translation, and an incorrect target sentence, which only differs from the correct one in a pronoun. And the model should assign higher confidence or lower perplexity to the correct one, and we calculate the accuracy. Okay, so that's all for the experimental setups. Then let's look at the results. First, this bar graph showed the BLUE scores of the baseline transformer and the same transformer model plus our pronoun data augmentation method. The scores are the average of 5 models trained with different random seeds, but we observe no significant difference between them in terms of the BLUE score. So in our proposed method, we add some artificial data, but it doesn't hurt the overall translation quality. And unfortunately, nor does it improve the overall translation quality, the BLUE score. So next, let's look at the pronoun translation evaluation accuracy. So this graph shows, okay, this is the score evaluated on that data set. This graph shows around 9 points improvement in the accuracy of pronoun translation by our method. So our method does improve the model's ability of zero pronoun translation. Okay, this is a good news. So we've confirmed that our method works in our setting. Let's look at what happens when combining another method to improve zero pronoun translation. This already appeared in previous presentations. So 2-to-1 model. 2-to-1 model refers to a model where the input is augmented with a previous source sentence, like this. So it's essentially a normal NMT system with a longer input. But the model is not asked to translate the whole input, but only translate the latter part. This is known to improve zero pronoun translation because sometimes the previous source sentence has information on the dropped pronouns. Like in this example, the previous source context have the correct subject, like it is not zero pronoun, but explicitly says I, boku wa in Japanese. So the model might be able to use that information to correctly translate zero pronoun in the latter part. So let's see what happens when we combine this 2-to-1 model with our zero pronoun data augmentation. Here are the results. Again, this does not improve BLUE scores. So let's look at zero pronoun translation. Compared to the 1-to-1 baseline, this 2-to-1 by itself improves zero pronoun translation. And when combined with zero pronoun augmentation, it further improves the score. But when compared to 1-to-1 plus augmentation, this 2-to-1 plus augmentation does not show improvement. So this is this is not what we expected, because both 2-to-1 and data augmentation improves zero pronoun translation. So when combined, we thought it would show an even higher score, but like it did not happen, like by comparing 1-to-1 plus per aug and 2-to-1 plus per aug. We think this might be because longer inputs in 2-to-1 models make it harder for the model to learn the correlation between local context and zero pronoun translation, because the input is longer, and maybe the model had a hard time to like figure out which part I should focus when translating pronouns in that longer input. So the two methods, 2-to-1 and augmentation, may not have much synergy. Okay, now we've seen the performance of our proposed method. Let's finish off with the analysis to understand the relation between zero pronouns and local context in Japanese. So the purpose of this analysis is to understand what kind of local context gives clues to zero pronoun translation. So here is what we did. I'll briefly go over the analysis method. So first, we need to detect like sentences, Japanese sentences with zero pronouns. Ideally, if we have a high quality sentence analyzer in Japanese, we can do that, like detecting zero pronouns, but I couldn't find any good analyzer for that purpose, so we utilized the parallel sentence. We first learn word alignment in the training data, and when the English pronoun is aligned to null, we regard the sentence to have zero pronoun. Okay, and then with this method, we count the number of zero pronouns and non-zero pronouns, and here is the graph. So you can see like those frequent pronouns like I, you, it are very much often expressed as zero pronouns in Japanese in the conversation. So yeah, this is what we observed. And next, after extracting sentences with zero pronouns, we have to detect, okay, what kind of local context is associated with the zero pronoun. We first extract the head node of the English pronoun in the dependency tree, and then look at the aligned Japanese word. So we regard these aligned Japanese words as predicate of the zero pronoun and extract these blue words as local context. And then we use that local context to train a linear classifier to predict zero pronoun. And then look at the weights, like feature importance of the classifier to see what kind of local context is predictive for certain kinds of pronoun. Here's a result. Like for the first person singular, like I, to predict this kind of zero pronoun, these words are very informative, like interjectory particle. Like these are, how could I say? So these are kind of interjection, which is appended at the end of sentence. So I cannot explain why, but when I hear these words at the end of sentence, I feel that the subject is the speaker themselves. So the subject is I. But of course, it is not always. And the expressions for wish in daily conversation, these expressions like for wish are often used with the first person singular as a subject. Well, like in the state of zero pronoun, I mean. We also extracted verbs that characterize the zero pronoun I. There are a lot of verbs that concerns with recognition of the speaker, like I think, or I remember, or I understand, I feel in Japanese, these blue words, 思う, わかる, something. This is reasonable because you only perceive your own recognition. It is much more often to say like, I think than you think in Japanese. Other type of local context is humble language. In Japanese language, we often use certain kinds of expressions to indicate social relationship between the speaker and the listener. So this humble language is only used to humble the speaker themselves. Of course, they never humble other people. So this is kind of intuitive. Okay. I think we are running out of time, so let's skip those slides. You can check the example in our paper as well. So in summary, we tackle the problem of zero pronoun translation in the Japanese English translation task. We propose zero pronoun data augmentation to facilitate the model learning the correlation between local context and zero pronouns. And in experiment, we demonstrated its effectiveness. The experiment was in the business conversation domain and zero pronoun translation of the data set. Okay, that's all for my presentation. Thank you for listening.
Thank you for the nice talk. So I'll accept one or two questions. Are there any questions from audience?
Yes, I have one confirmation.
Sure.
It's a nice talk. Actually, Japanese grammar is very close to Myanmar language grammar. Really interesting. So let me confirm one thing. When you make a data accommodation, so you only use the Japanese language. Is it correct?
Yes, only use Japanese. What do you mean by use? Like there, it is a parallel data. Yeah.
Yeah. So when you extract the or making the data accommodation for zero pronoun, you made a fake data through the Japanese sentence, right?
Yes, yes. We didn't like do something with English sentence.
I see. So my comment is if you also see the target language or English language, you can get more augmented data, and
probably yes.
And that will be affect very much according to my small experiment for my language. Because when I try to do for my language in locally in our lab, I found it's really depend on the English language or the translated language. Sometimes we got a lot of information, although we don't have. I mean, though my language don't have a pronoun in the sentence. So that's my comment.
Okay, thank you for your comment.
Is there any other question? So time is over. So thank you, Lee. So let's move the third presentation.
Okay, thank you.
Thank you. Third presentation is evaluation scheme of focal translation for Japanese partially amended status. Yamakoshi, could you start the presentation? Yes, I can see the slide.
Okay. So can you see the slide correctly?
Yes. Yes,
thank
I
you.
can hear you on the slide.
Okay, thank you very much. So hello everyone. My name is Takahiro Yamakoshi from Nagoya University, Japan. Today I'd like to talk about our research named Evaluation Scheme of Focal Translation for Japanese Partially Amended Statute. So this is the agenda of this talk. The first topic is the background of our research. So our research is going to help the global publicization of Japanese statute. So this is this is a kind of a very specific field, specific domain. Anyway, so let me introduce the current situation of the global publicization of Japanese statute first. Actually, so currently, the Japanese government is providing a web service named Japanese Law Translation Database System, JLT. Here, we can find some of Japanese statute with its English translation, so in JLT, and then these translations can be used for international readers to refer the Japanese statute in English. However, so statute will sometimes be amended. So to change it's update the contents of statute to cope with the change of society. And so once we have a post amendment Japanese statute, then its contents and its translation in JLT will naturally desynchronize. And actually, this desynchronization is a very severe problem in the current operation of JLT because more than 75% of statute in JLT is in this state. To solve this problem, of course, so we need to translate the post-amendment Japanese statute to English. Then so we update the contents in JLT. However, in the current operation of JLT, the human translators translate this post-amendment Japanese statute, and so they translate the whole contents. So that's why the translation operation is not so effective. So that's why the desynchronization is happening. From this background, so we try to establish an automatic translation method for the post-amendment statutory sentences. So that is the background. And next, I'd like to discuss about the amendment types to identify our research. And actually, the amendment has two types. The first type is the fully amendment. Here we replace the whole statute with the new contents like this figure. And the second type is partial amendment. Here we replace some part of a statute with the new contents. And among these two types, so we focus on partial amendment because it is most frequent. So actually, almost all of the statute, almost all of amendment made in Japan is a partial amendment. And even if we look at the all enactment, so making laws in the Japanese government, so more than 70% of enactments is actually partial amendment. So that is coping with translation or partial amendments is quite important for the global publicization of Japanese statute. And next, so we discussed how to evaluate post-amendment translation. So yeah, so to discuss this, so we use this toy example. So we have a pre-amendment translation. The request shall be made in the document stating the effect to the extent. And then so we have an instruction of amendment. So the request now should also contain reasons of the extent instead of the effect of the extent. So in this case, we consider that we have two candidates of post-amendment translation. The first one is the request shall be made in a document stating the effect and the reasons of the extent. And the second one is the request shall be made in writing describing the effect and the reasons of the extent. And so from the viewpoint of fluency and adequacy, that are the traditional criteria of automatic translation. Actually, both of the sentences are fluent and adequate. In terms of that, they mean the intent of amendment. So using the fluency and adequacy, so we need to evaluate them equally. But so now we doubt that we truly evaluate them equally in for the post-amendment translation. So to answer this question, so we think about the demand for post-amendment translation for the users and editors of such translation. So from the viewpoint of the readers for the post-amendment translation, they will think that the translation should be easy to identify amended expressions because the readers need to understand the contents of amendment to identify its contents. And so from the viewpoint of this demand, so the readers will think, well, the readers will misunderstand by reading the second candidate because we changed the verb. For example, we changed the verb stating to describing. Also, these verbs are synonyms, so the meaning hasn't changed. But the readers may misunderstand that the terminology in this statute has been changed during this amendment. And so from the viewpoint of the editors, they will require the translation should be easy to post-edit. And in this case, especially in this case, reusing the pre-amendment translation is effective because the contents of pre-amendment translation is already reviewed, and so that they are publicized in JLT. So from this viewpoint, the editors will think the first candidate should be good, should be better, because it has much more retention in the pre-amendment translation. So from the both demand, the first candidate should meet the demand much more. So that's what we need. We try to choose the first candidate for the post-amendment translation. And to do this, so we need the third requirement in post-amendment translation, in addition to the fluency and adequacy. So we call this focality. And so focal translation in our definition is to update on the expressions regarding the amendment where we should retain not affected expressions as they were. So, from the previous example, we use the focality to choose the first candidate for the better post-amendment translation. So which update the expressions regarding the amendment only, and it retains not affected expressions. So the objective in our study, so we call again, is to establish the evaluation scheme for post-amendment translation. And so more concretely, so we try to propose the way to evaluate focality. That is important criteria for the post-amendment translation. And so that was the explanation of our background. And next, so we will talk about the evaluation scheme. Actually, so we have developed existing focality metric, which evaluate the focality. So we call this focality score. And so this previous focality score has two components, the recall of unchanged n-grams in output to evaluate how the system retained unchanged expressions. And it contains second component, it is a penalty on redundant output. But actually, so its primary component is this recall. So this evaluates how the system retained unchanged expressions. And so we show one calculation example by using the focality score. So in this example, so we change the number of people in this amendment like this. And so we assume that we have two system outputs. The one is each of them has an error in the unchanged part and changed part, so respectively. And by calculating the score, focality score, the focality score will output these values for each system output. Here, the focality score didn't penalize to the second output because the error in the changed part. And actually, so we consider this is actually okay or not. To discuss this behavior, so we use the more extreme example. So this is also third out, which is the third system output. So in this case, this output has a full of errors in the changed part, but it doesn't have any error in the unchanged part. So that's why the focality score is still the highest one. However, in the focal translation, so we need to update expressions correctly. So that way, this kind of no penalty on the updated expressions is actually it's not good. So we need to penalize even this kind of error to evaluate focality more well. So from this problem, so we updated our focality metric. So we call this our evaluation metric ISDIT, inclusive score for differential translation. So the ISDIT consists of two components, the precision of output n-grams. Here we calculate the quality of changed expressions. And then so we reuse the record of unchanged n-grams in output to evaluate the unchanged expressions. And so with the both of them, so we evaluate both the changed and unchanged expressions. And so with our in the previous example, so our new ISDIT can penalize the both of the system output regardless of the error. So it embeds. So finally, I'd like to talk about the experiment of our evaluation schema. So here, the objective of our experiment is to assess the performance of our new ISDIT. So to assess the ISDIT, so we used this number of training data and also this number of test data. Here, so we newly compiled the test data to meet the focality requirement. So we newly translate the post-amended sentences, yes, to meet the focality requirement. And so we compared this method. So first we used the naive SMT and the NMT system. Then so we used the template-aware SMT system. This can fix translations. And so the last two methods are the combination of the template-aware SMT and the NMT method. And so this is the result of the evaluation. So we compared the scores output by the focality and so then ISDIT. And then so first we look at the focality score. And then so we can find that the focality score, so output the highest score for the template-aware SMT method. And then so we assess the result was reasonable or not. Now, to assess the result, so we rate the system output for each system, and then so we find some tendencies of translation. So actually the template-aware SMT method has a tendency like so containing so severe errors in the change expressions. So like this one. So maybe so this is because of word alignment, which is used in the template-aware SMT system. And so the combined method, this is actually based on NMT output. But so this chose this output, so rather fluent sentences. However, this sometimes choose so synonyms for unchanged expressions like this. So that's why, yes. But however, so in totally speaking, the quality of template-aware SMT, so the combination method should be good. And so going to back to the result, the ISDIT, actually evaluated the best value to the combined method. So this is a rather maybe so we there is a bias or evaluation fiber. So we consider that our ISDIT so did some more reasonable so evaluation. And so let me summarize my presentation. So we have proposed a scheme for Japanese partially amended translations. Here, so we discussed that so we need a new criterion for evaluating the partial amendment translations, so which is the focality. And for the focality, so we have developed a new metric which focuses both changed and unchanged expressions. And actually, so we made a new dataset for the evaluation. And this we observed a characteristic of translation method with a scheme. And as for the future works, so we need to increase the size of our corpus, and because actually, yeah, the corpus is quite small. And then we try to apply the scheme to other domains like contract or technical document or product manuals. So this is the end of the talk. Thank you for listening.
Thank you for the nice talks. So are there any questions? If there's no questions, I have some questions.
Okay.
I want to see the slide page 6.
Page 6, right?
Yeah. Yeah. So for the amendment, how to decide the phrase? So the second example is the fact of the accident is modified to the fact and the reasons. However, of the accident and the reasons, that Z is the same, and maybe the other reasons, the phrase of and the reasons should be amended. So how to decide the phrase or for amendment? Is the words level or phrase level?
So it's a question, but so like so from the amendment instruction, so how to decide how to say the extent of amendment, so like so phrase level or word level. Actually, so it depends on the each instance of amendment. So some amendment can be some amendment. For some amendment, so we can just change some only one word, or so some other cases. So we need to add, so like a phrase, or so even if we need to add, so like yeah, so much longer phrases. So it depends on each each instance of instruction. So
So does it match your question?
Yeah, okay. And so in relation with this question,
yes,
amendment or human amendment, or the human amendment, human can see the context information. So I mean
yes.
that if answer is yes, so could you think about the use of context information for the model?
Yes, actually, so as you think, so human translator will read the whole statute, and so we need to the context outside the sentence to translate correctly. So yes, so that is the need of context. So document level context is quite important, and that is the next future work. Yeah. So thank you for your insight. Thank you for your insight.
Thank you. And are there any questions? So thank you, Yamakoshi. So I'll move to the last presentation in this session. The last presentation is joint optimization of tokenization and downstream model. Hiraoka, could you start the presentation?
Sure.
Yeah,
now I share my screen.
Yeah, I can see the screen and I can hear you.
Okay, so I will talk about my paper, joint optimization of tokenization and downstream model. Okay, so I'm the first author, Tatsuya Hiraoka. So thank you for giving the very good opportunity to present my findings paper in this great workshop. First, I will tell you our research motivation. This figure shows general architecture of NLP. To solve the downstream task like text classification, we should tokenize the text corpus into a sequence of words, as you know. In such a pipeline system, many researchers report that the performance of the downstream model will be improved if we use the appropriate tokenization for the downstream task. However, in practice, it is quite difficult to find the appropriate tokenization because it highly depends on the task and parameters of downstream model. Also, we must select the tokenization as pre-processing before the training of the downstream model. So now here is a huge gap between the pre-processing and the downstream model in terms of the ideal tokenization. In other words, we must select the tokenization even though the appropriate tokenization highly depends on the downstream model. So to bridge this gap, we proposed an idea to update both the tokenizer and the downstream model simultaneously during the training phase. Our method updates the tokenizer to yield more useful tokenization for the training of the downstream model. Thanks for this framework, now we are set free from the problem to take a lot of time to select an appropriate tokenization. So now I am talking about the basic strategy of our method. Again, the goal of this research is to acquire the appropriate tokenization depending on the downstream model. In this research, we assume that the appropriate tokenization is a tokenization that brings a lower loss value for the downstream model. In this example, the downstream task is sentiment classification. That is one of the text classification tasks. So we can use neural text classifier like something use LSTM. Also, for the loss function, we can employ the cross entropy loss against the correct label. By the way, when considering the case where we input the different tokenization of the sentence into the downstream model, in such case, we must get different outputs depending on the tokenization. For example, when this tokenization is used for the input, the loss value becomes 0.22, while the other tokenization reads the different loss value like this. As mentioned before, we assume that appropriate tokenization, say an ideal tokenization, is that tokenization with the minimum loss value among the candidates. So we want the architecture to obtain such the ideal tokenization automatically. To realize this system, we create multiple tokenization as shown in this figure, and update the tokenizer to assign the higher probability to the tokenization that reads the lower loss value among the candidates. In this work, we employ a neural unicorn language model as a tokenizer. This calculates the word probability with neural networks. Depending on the word probability calculated by this language model, we obtain the n best candidates of the tokenization. For example, we show 3 best tokenization in this figure. We calculate the probability of the tokenization by product of the probabilities of words comprising the tokenization, as like general unicorn language model. To update this tokenizer or language model, using the loss value of the downstream model, we weight the loss values with the corresponding tokenization probabilities. Here, we normalize the probabilities of tokenization so that the sum of them becomes 1. We treat the weighted sum of the loss values as the final loss value to train both the downstream model and neural unicorn language model simultaneously. Since we calculated probability of tokenization with neural network, we can obtain the gradient for the tokenizer. In other words, applying the backpropagation for the weighted sum of loss, we can update not only the downstream model to predict the correct level, but also we can update the tokenizer to assign the higher probability for the tokenization corresponding to the lower loss value. By performing this training process for the entire dataset iteratively, we can obtain the tokenizer assigning the higher probability to the tokenization that reads the lower loss values. In this training, we can use various downstream model and loss functions if we can obtain the loss value from them. So our proposed method is applicable to various NLP tasks. For example, in the case of machine translation, we can optimize the source size tokenization by employing a transformer as the downstream model and use target sentence as the correct data. Also, by using same architecture for the target side, we can optimize the tokenization of both sides, source and target languages simultaneously. After the training of our method, the tokenizer can assign the higher probability to appropriate tokenization for the downstream model. So for the test phase, we only use 1 best tokenization for the input of the trained downstream model. We can obtain the 1 best tokenization with the VW algorithm, so the computation cost is not so high. So I have to explain the initialization of tokenizer. For the proposed method, we can optimize the tokenization from the random initialization, but we don't recommend this option because the optimized tokenization highly depends on the initialization, and this causes unstable performance on the downstream task. Therefore, we initialize the tokenizer in our method with the existing tokenization toolkit named sentence piece. Yeah, sentence piece is a well-known tokenization tool for the unsupervised training of unicorn language model. And we use the trained sentence piece model to initialize our model's vocabulary and word probability. So we conducted, move on to the experimental results. We conducted the experiments on the text classification and machine translation, and this slide summarizes the experiments on each task. The experimental results show that the proposed method joint optimization improves the downstream performance over the entire dataset on both tasks. I will explain the detailed result in the rest of presentation. First, I explain the result of text classification. We used the neural text classifier with bias DN and compare the F1 score of models trained on sentence species tokenization and our tokenization. There are some tasks for the text classification. We used short text SNS, Twitter for Japanese and English, and Weibo for Chinese for the sentiment analysis. And genre prediction is a task to predict the product genre from the review text on e-commerce web service like Amazon. Similarly, rating prediction is a task to predict the rating of the review from the review text. Yeah, SNRI is a well-known dataset. So, and experiment, for the SNRI, there is a 2 inputs. So, yeah, it's a quite a bit different setting, but it is also the text classification. The experimental results show that the performance of proposed method outperforms the baseline sentence piece. The result indicate that that our method contributes to improvement of the performance by optimizing word segmentation on multiple tasks of text classification in several languages. Okay, so here is the result of experiment on machine translation task. In the machine translation task, we employ transformer for the downstream model, and we compare the Bruce scores of sentence piece and a method. In this presentation, we report the scores on 3 language pairs from IWSUT and WMT Coppola. Yeah, the original paper includes the other experimental settings, so please refer to my paper if you are interested in. So, and yeah, I have to explain how to read this table because it is a bit confusing. In the machine translation task, yeah, as you know, there are 2 languages on source and the target side. Therefore, we have some options of experimental settings. I mean, only optimizing the tokenization of the single side of languages like source only or target only. And the other choice is optimizing both sides simultaneously. So we highlight the tokenization method used for the source side with blue and target side with red. For example, the second column of the result part means an experimental setting where we optimize only source side with our method. And we use original tokenization by sentence piece for the target side. Now I highlighted the experimental setting that uses our method with red frame. And also we highlighted the scores of outperforming the baseline method with the green bar color. Here we consider that the baseline is a setting where we use sentence piece tokenization for both sides of languages. From the result, we can say that most experimental setting with the experiment setting with our method surpasses the baseline score, and our method contributes to improvement of the scores on the machine translation task. In addition, the experimental results tell that the setting where we optimize only one side of language often achieves the highest performance. Especially optimizing only the target side is effective for the machine translation task. In contrast, when using the proposed method for both source and target side, the performance of machine translation is not so high compared to one-side setting. We consider that this is because it is difficult to optimize tokenization on the both language at the same time. And the training of the downstream model becomes unstable to harm the final performance. So we introduced the examples of optimized tokenization on machine translation tasks. We employed Chinese to English and English to Chinese pairs, and we optimized on the English side using our method. And then we take the difference of tokenization depending on the situation that English is on source side or target side. In the top of this slide, we show the tokenization example optimized in English to Chinese machine translation. When English is on the source side, the proposed method tokenizes the sentence into tiny units by splitting suffixes from the initial tokenization. For example, our method cut off the subword do from the word don't and split alphabet E from half. In fact, the length of tokenization, I mean, the number of tokens in the tokenized sentence is 1.35 longer than 1.35 times longer than the original tokenization by sentence piece. The bottom part of this slide shows that the tokenization example optimized on the target side. When we optimize English sentence in the target side of machine translation, the proposed method does not change the tokenization hardware from the initial tokenization. For example, the proposed method splits the past tense suffix ed from the words separated, but the total length of the sentence is not changed. In terms of the tokenization granularity, the number of tokens in the optimized tokenization is 0.99 times longer than the initial tokenization. This means that the optimized tokenization is a bit shorter than the original one. We consider that this tendency is related to nature of machine translation models. When the number of target sequence is large, it is difficult for the decoder to generate long sequences correctly. Thus, the proposed method avoids such a long sequence that makes the decoding process more difficult. In contrast, the length of tokenization on the source side is not directly related to the decoding process. So the proposed method tends to make more shorter words and longer sequences. This example shows that the optimized tokenization on the source side is different from the target side. And this implies that the proposed method can optimize tokenization depending on nature of the downstream model. Okay, overviewing this research, we propose a method to optimize tokenization depending on the downstream corpus and the downstream model. Experimental results show that our method has good effect on the text classification and machine translation. That's all of my presentation. Thank you for your attention.
Thank you for the nice talk. So are there any questions from audience?
Hi, can I have a question?
Please.
Sure.
Okay, so so you're pursuing hard tokenization, so explicitly tokenizing a sentence, but I'm recently curious about soft tokenization, like input characters into the model, and the model like automatically learns how to combine them. So what do you think about the soft tokenization? Do you have any opinions or impression about those methods?
Yeah, this is a very good question. Yeah, recently the soft tokenization, like a Shareformer, soft tokenization is a very good idea for the model to improve the performance of the performance. But soft tokenization is a bit difficult to understand for human to understand the tokenization. So to analyze the morphology or tokenization for the machine, I mean AI, hard tokenization is useful for such analysis. But in terms of the performance, soft tokenization is very good idea. This is my comment.
Oh, thank you. Okay, I understand. Yeah, hard tokenization has more interpretability. Okay, thank you.
Yeah, thank you very much. Yeah, if soft tokenization focuses on the understandability, the research becomes more useful for humans. Thank you very much.
Any other questions? So I have some questions.
Sure.
The first question is maybe your idea is depend on the domain or any other kind of different features. even in the same language data. So when I want to multitask learning, can I use your idea? So how to implement the best way for each domain?
Yeah, very good question again. This is such I also interested in the multitask setting for our methods. And as you mentioned, as you pointed, this method focuses on the optimization for the specialized target domain or target corpus. So if we use our method for the multitask setting, I expect the model to acquire the tokenization that is widely used for the multitasks. It maybe becomes the same tokenization as sentence piece or other unigram models. But I didn't this setting, so I didn't conduct this experiment in this setting. So I cannot answer the detailed results.
Okay.
I'm sorry.
Okay. And moreover, in the sentence piece or any other tokenization, maybe some models use share vocabularies on source and target side. So when share the vocabulary in your idea your method can be improved or not. So maybe the decoder is your results shows that decoder is can be improved, but encoder is not so good results, right? So how to
So thank you very much. Yes, I can. Our method can be is capable to apply to such shared vocabulary, and when sharing the vocabulary, the performance becomes stable, and but the improvement of the performance a bit small than the separated vocabulary. So but also I didn't analyze in detail about this experiment. So I just say this observation or only this observation.
Okay, thanks. So any other questions?
I have a short comment based on the Chairperson Mino-san question. How about if we consider pre-training in advance for the multi downstream test? I think it is possible.
Sorry, question?
How about pre-training the segmenta in advance? Let's say we were pre-trained for downstream test 1, downstream test 2, downstream test 3 in advance, then we can apply. Is it possible, right?
Yes. You mean the pre-training the downstream model and then optimize the tokenization, right?
Yeah, in practically or in engineering way, I think that might be more suitable according to my knowledge.
Yes. Our method is applicable to such technique.
Yeah, thank you. Nice talk. Yeah, I enjoyed very much.
Yes, thank you very much. Yes, such the optimizing tokenization after the trained downstream model is written in the paper. So please refer to the paper if you are interested in. Thank you very much.
Thank you for the questions and thank you for answering the questions. So the time is over. So I want to close this session. Thank you. So thank you for the all presenter and thank you for the all participants. So I want to change the chair to Nakazawa-san. Could you announce the lunch break?
Okay, so let's start the afternoon session from 1 p.m. as scheduled. Thank you very much.